Okay, let's start again. We are here today to explore and discuss the latest advancement and challenges in visual perceptions, particularly in the crowded environments. And our goal is to foster collaborations, share knowledge, and inspire new research in this critical field. So this is the Jack robot. This is like the spirit animal of the GRDB dataset. And it boasts a range of modalities, including stereo, cylindrical, RGB cameras, 3D point cloud from two velodyne lidars, IMU, GPS, and the audio microphone. And throughout the workshop, we will cover a range of topics, including lidar segmentation, self-supervised learning, embodied navigation, and urban simulation for embodied AI research. So our programs, you can scan the QR code there to get access to our programs. And we also have a poster session in the middle of the workshop to showcase the research. So I would like to take a moment to thank our organizing team for their hard work and support in making this workshop possible. A big thanks to all of you here joining us today, even in person or online. And your participation and contribution are what make this workshop a valuable experience for everyone. So without further waiting, I'm thrilled to introduce Dr. Laura Liu-Taisei, a leading expert in the field of computer vision. So Dr. Liu-Taisei is currently a senior research manager at NVIDIA and an adjunct professor at the Technical University of Munich, where she leads the Dynamic Vision and Learning Group, with a rich background in that includes the tenure track professorship at TUM, postdoctoral research at ETH Zurich, and she obtained her PhD from the Leibniz University of Hanover. She has made significant contributions to the field. So please join us. Welcome Dr. Laura Liu-Taisei.
Okay. Okay. Awesome. Yeah, thanks for the introduction. So today I want to talk about our works in open world segmentation and tracking in 3D. So essentially how to bring all the nice and cool stuff that we've been doing in detection and segmentation and tracking into the open world, and especially using other sensors like integrating LiDAR and making sure that all the knowledge that we have in the images can also be transferred into 3D. So yeah, the task that we're interested in is basically going towards embodied autonomous agents.
Sure.
And yes?
Should share just the slides only.
Oh, I'm sharing. Okay.
Yeah.
Wait. Oh, but I cannot swap.
Just Zoom on Zoom. Yeah.
Okay.
Just, new share. Yeah, new share. And select the slides only.
I did select the slides. Should I just select the desktop?
Layout was that.
Wait, let me just try like that. No, this
Okay,
is
now I see your slide.
Is it?
Yeah, yeah. Okay.
Now it works? Okay, good. Okay, so I hope now it works also for the Zoom people. Awesome. So yeah, we want to essentially go towards building autonomous agents, right? Like autonomous cars, robots, and so on. And for this, there are several perception tasks that we're interested in, right? So we want to give these autonomous agents the ability to understand what is around them, the ability to predict how these other agents are going to move, to anticipate their motion, and also to understand where the actual agent is, right? Like location in a big scenario. And in this talk, I'm not going to talk about the localization problem, which is also something that we're deeply invested in my research team. I'm going to talk more about trying to understand what is around these autonomous agents, and especially how do they move. So this is what we call in general dynamic scene understanding. And I just want to make kind of an initial motivational plot about how much data do we actually need to tackle the task of dynamic scene understanding. So on the y-axis, we have the task going from least complex to more complex, and on the x-axis, the number of classes going from just a handful of classes all the way to the open world. So let's start with, a classic task of semantic segmentation, right? This is about assigning a semantic class to every pixel in the image. This is pretty much solved for a handful of classes, even for thousands of classes, right? We have data for that. We train our models. Things are starting to work very robustly nowadays. So this is a problem that we know how to tackle. We can then move to slightly more complex problems, like, for example, panoptic segmentation, in which we not only need to detect the semantic classes, but we also want to differentiate between the different instances of each semantic class. And this is also a problem that one can tackle in a supervised way for a handful or even thousands of classes. Now, things start to get interesting when we add the temporal domain, right? When we want to do multiple object tracking and segmentation. We can also create data sets for that, but we will see later, it's quite annoying to annotate videos and to get the temporal consistency necessary. But this is not, like, neither of these tasks is really what I'm here to talk about, right? Like, what I want to get to is actually for the panoptic segmentation, right? So we want to take all the good stuff from panoptic segmentation, from tracking, and take it into the 3D world and really embed other sensors, like, for example, LiDAR sensors. And this we want to do not for a handful of classes, not for even thousands of classes, but we want to do it in the open world, right? So anything that comes in contact with our sensor is something that we want to understand, we want to segment, and we want to assign an instance to it. So how do we tackle this task in terms of data? Well, for the task of semantic segmentation for up to thousands of classes, we're just like, sure, let's get some data, train our model, problem solved. Oh, is requesting remote control? Okay, something happened on Zoom, but so I'm getting requests for remote control. I don't know why.
It's not me. Just click on.
Okay.
Yeah.
I cannot continue the talk though. Like, it just appear and I decline it, but it keeps appearing.
Sure. Who's this guy?
Yeah.
Should be good.
Okay, should be good. All right. So even for multiple, okay, now it's happening again. For robotics, for autonomous driving applications. So why not actually specifically find a solution for those? So this is where the second word comes in, with the concept of what moves together belong together, right? So if I can cluster moving points in the LiDAR space, I can potentially find new object categories, even if Click doesn't understand and cannot give a name to that object. So this is kind of the problem statement that we have. We have as input a very small set of labeled LiDAR streams. So we do need a small set of labeled LiDAR streams, and we have a huge set of unlabeled LiDAR streams. And what we want to do is we want to basically train an object detector that is going to work for objects that are observed moving. So for example, in this case, I'm depicting the output that we would like to get for cars. So let's see how one would train this object detector given these two types of input. So in our method, what we propose is, again, a pseudo label generation method, but slightly different pseudo labels here. So here, we're going to have a first step, which is going to be the cyan color step at the left, which is basically some form of pre-processing of the LiDAR point cloud and trajectory prediction. So here, we're working with scene flow. We actually want to obtain the trajectories of the LiDAR points and not LiDAR points in 3D. So once we have these trajectories, we are going to cluster them by motion with our method Somoli, and then we're going to finally extract the bounding boxes. So this first step is something that is present in the literature. So this is something that we just took over. The second step, Somoli, is our contribution. This step of motion clustering is usually done with DB-scan, and here we think that with machine learning, we can actually have a much better shot at it. At this time, then, we simply take those bounding boxes and we use them as training data for, your favorite off-the-shelf detector. In our case, we train point killers on our pseudo-label detections. Okay, so how does this clustering really work? So as I said, many methods are using DB-scan, and this has worked well for the segment anything in LiDAR, for our point cloud segmentation, but we wanted to do better here, right? Because when we do this motion clustering, if we don't have very, very accurate clustering, we're in danger of just getting completely wrong bounding boxes. So what we're going to do is we're going to propose to do this with graph neural networks, right? So we're going to create a graph where the nodes are these point trajectories that I was talking about, and the edges connect these trajectories that might belong to the same object. So you can imagine that a car has, for example, 20 LiDAR point clouds that are following the car and are representing the car. And what we actually would want our GNN to do is to say that these 20 trajectories belong to the same object because they are moving in a coherent way. Now, in the GNN, we're going to have a series of message passing steps, which is essentially just nodes and edges communicating their features and updating their features based on the information from the neighbors. And this is essentially what allows the trajectories to see how nearby trajectories are moving and to decide whether, the motion is similar to their own motion or not. And finally, we're going to have, let's say the loss that we're going to use to train this GNN is going to be a classification loss, right? We're going to classify edges into active, meaning that two nodes, two point trajectories belong together, they belong to the same object, or inactive if the 2 point trajectories do not belong to the same object. We're going to have some correlation clustering to make sure that all the constraints are satisfied, and then we're going to extract bounding boxes from those point trajectories. So let's see some interesting results. Well, first of all, I want to know essentially how am I doing with for the task of object detection. That's the first thing. And the second thing I want to do is see how good am I at cross dataset generalization. So let's go for the first results. So here we are plotting our results in green. This is Somoli. You can look at the precision and recall. These are the third and fourth columns, and the AP value. This is the fifth column. And you can compare it, for example, with the previous row. That's the yellow one, which is the DB-scan baseline, which is was state of the art at the time. And you can see at the top the gap with respect to training with ground truth detections, right? So of course there's going to be a gap always, right? I mean, we don't assume that we're going to get the exact same accuracy, but we see that it's already quite up there. And of course, like the main point here is that the improvement over prior state of the art is actually really large. I mean, we're talking about almost 14 points AP. The other point that we wanted to test was generalization, right? So what if I train on Waymo data and then I test on Argoverse, for example? So one can imagine that there's tons of differences between these two data sets, right? Like the point distribution is completely different because the sensor is different. So it might as well be that the network that I used and trained on Waymo doesn't really generalize on Argoverse. Now, the cool thing is that this GNN is actually comparing trajectories. And so it does a pretty good job at actually generalizing, right? So the point distribution doesn't affect results so much. And the even cooler thing is that we can actually detect objects that we never saw during train time. So here we're seeing some objects on Argoverse, which are trucks and buses, which were never seen during training on the Waymo dataset. And we can still detect those, right? Because I mean, essentially what we're learning is to do motion clustering. So it doesn't really depend on the semantic class of the object that we're trying to cluster. So these are some results that we obtained on Waymo for car detection. And these are some results on Argoverse, noting that we never trained for this sensor, right? So we have never seen, the GNN has never seen this sensor before. It has never been trained on that. And you can see that it still does a pretty good job. And again, this doesn't really need to be perfect, right? I mean, these are just pseudo labels. So you can just pseudo label tons of data and then train your detector. And it doesn't matter if you missed a few spots here and there, because this is just training data, right? So you can really scale it up. And you can see, for example, that we can also detect people and smaller objects, and this still works in a quite consistent way. Okay, so yeah, in this talk, I just wanted to sort of write a couple of take-home messages. First one is that pseudo labeling is a really powerful tool to leverage strong 2D foundation models for 3D tasks. So there is no need to annotate everything. One should really try to leverage the information that we already have present in the data sets. Also, the fact that geometric and 3D motion fields are still very much to be explored. And finally, is that, you know, we just want to open up possibilities in 3D and especially in 4D processing without requiring label data, right? And we actually show that this starts to be possible now. So I think this is something that we should really actively work towards. Okay, so with that, yeah, I'm at the end of my talk. If you have any questions, I'll be happy to answer them.
Any question? I have some questions.
The first half, there's one recurring, let's say, confidence with detecting objects in the environment. What can you do to like prevent that from happening?
Oh, I mean, tons of things, right? I mean, this was just like basically on a frame by frame basis. I'm showing you the result without any filtering, without looking at any consistency. But we're now working towards a 4D version, right? So even just naively averaging the results across 5 frames would look much better. This is just, you know, to show you, okay, what are the raw results, right? But of course, like adding temporal consistency would be trivial. Yeah.
Any other question? Maybe I can start. I have one question. Or a very interesting idea how we can kind of make ourselves less dependent on annotation, which we know what's a complexity for that. The idea of the moving clustering the moving object, how we can deal with if, for example, there's 2 pedestrians moving side by side. What's your take on message is if we want to really now deal with those, not get the one, but try to generate, because we don't want in the crowded scenario, get the only box for the crowd, will affect the training as well. What's your take on how we can deal with these cases as well?
Yeah, no, that's a really great question, right? So of course, if you have like 2 people that are moving exactly in the same way together for the entire sequence, you're going to detect it as a single object right now, right?
I see.
So one thing that we have been exploring is actually to include shape information, right? So you are training the GNN. We wanted to train it in an object agnostic way, right? So that I can train on people and still, you know, be able to cluster car trajectories and bus trajectories. But if you are, let's say, willing to depend a little bit more on the semantics, then you can include a little bit of shape, right, in the GNN. So basically, just some shape features in the nodes would do. And then essentially, what the clustering is learning is that there are boundaries to objects, right? And this is all in the data. So you then need a little bit more data to train this GNN. That is true. It doesn't generalize to so many classes, but definitely it does people, car much better.
I see.
Yeah.
I see. Yes.
Yeah, quick question on the first part. It's I think the scale issue with like the monocular camera is like a huge problem for 3D, and I just wondering if there is any like attempts that has been done to by like instead assembling like another vision foundation model like monocular tabs, like that's anything like Midas to help to like improve like the projection of the like image like foundation model feature to 3D. Is there anything that has been done?
We didn't really explore that. That might be an interesting thing to try. The thing is that some things you can really not solve, right? Like for example, like sometimes the cameras and the lidars, the viewpoints that they have are completely different, right? So I imagine that usually the lidar is more like on top than the cameras, right? And then, for example, you have a car and the lidar sees behind the car and the camera doesn't see behind the car. So there's no way that I can know what to project in the area that the lidar sees, right? And these are the problems that are more crucial right now. So this is not something that you would solve with a depth model, right? Because you run into the same problem that the depth depends on the camera viewpoint, which would also not see behind the car. So I think it's not solving the type of problems that we have, essentially. Yeah. Yeah.
So something I noticed in the first stage is that your model was not consistently, predicting every frame or detecting sort of objects in every frame, segmenting correctly.
Mm-hmm.
But the pieces that it did segment I never saw any class flipping or like getting the class wrong. Do you have any intuition as to why? I guess it seemed to have really good precision, but not the recall. And it's that, did you even run that on existing data sets to then see like how, what exactly those metrics were compared to ground truth in sense of?
Oh yeah, for sure. Yeah, I can go over the numbers. Let's say I don't plot all the numbers on this presentation because that would be like super boring. But I did wanted to point out to two results, right? Like, so the first one is that we're plotting in this case like PQ metrics and SQ metrics, and then PQ for things and PQ for stuff. And we can see the orange line are the results of the pseudo labels we train on. The green line are the results of the model, right? So the first thing that we're seeing is that the model does much better than the pseudo labels, right? Is able to absorb that noise. That is one thing. The second thing is that if we actually evaluate with a semantic oracle, meaning that we only evaluate segmentation and the semantic class, we take it from ground truth, then the performance, you see PQ 70.7 is super close to the performance trained on ground truth, which is PQ 71.8, right? And this is telling us like, and this is not the case, for example, when the semantic comes from the clip features, right? This is the green line there. And this is telling us that essentially we are getting the segmentation right. The segmentation is not the problem. The semantics are the problem, right? So the information that clip has is not enough for our problem. The segmentation is not really a problem. So, and this is a bit like similar to what is happening in the image domain, right? So it's not like we're having a completely different problem. It's the exact same problem that in the image domain. So this is kind of the crucial part that doesn't really work yet.
So even when you showed all classes, you're still relying on the clip labels?
Yes,
Like,
yes.
Continuing same question, I have similar. I would like to know your opinion about the concept of open word recognition.
Mm-hmm.
It's currently as a community we are looking into the clip, right? There's a twofold in the open word. Detect the object you don't know,
Mm-hmm.
recognize it, right? In detection, creating proposal is the one of the challenges, but for recognition, we are relying on the clip. We are ending up to have the whatever dictionary we have into the clip. Means if you are trying on the underwater cases, potentially we are not able to. What we need to focus? You believe from I know you're quite passionate about solving this open world, and this workshop is about that. But what do you believe as a researcher we need to more concentrate? Is it clip is the way to go, or what exactly? What would be kind of help us to have a better dictionary or some really unbounded dictionary of the recognition rather than the clip itself has a bounded recognition?
Yeah, it's definitely not open world, right? I mean, when people are like saying open world or zero shot, I mean, no, you're really relying on some annotated data, right? That's clear. I'm not really sure that we should give a label to everything that we detect and track, right? So for example, in the second work, we are detecting objects. We don't know what they are. I mean, in our case, we tried on cars, we tried on well-known objects because we can measure the accuracy, right? But if there was a rabbit in the middle of the road, you could still detect it and you could still track it, right? And maybe that's enough, right? Maybe I need to tell my AV that, you know, if there is something crossing the road, it has to stop. So I'm not really necessarily advocating for trying to understand and label every possible weird object in the scene, right? So I think relying on clip is okay because it gives us the necessary expressivity for AV, for robotics. Of course, if we look at underwater or medical imaging, that's something different, right? But I don't think it's necessarily a bad way forward.
Thank you. Is there any other question? If not, we can thank the speaker.
Yep. Right, the next is our workshop organizer presentations. So please welcome Dr. Hamid Rajtofiki. I think the problem with the Zoom is solved, and we can move on with the Zoom from now.
Share it with the Zoom as well.
Yeah, Zoom is on. Yep.
All right. Okay, thank you. And first, sorry, whatever happens in the Zoom, I think is out of our control. There we had kind of cyber attack. All right. This part I would like to a bit talk about the data set we created in the last few years, and then advantage of this data and what we did so far, what we are doing now, and what we will do in future, and where we are heading with this data set. The data set name is JRD, or the Jackrabbit data set and benchmark. And before I start this, I would like to highlight a couple of things about the data. Since 2019, when we start to collect and capture this data, we organized 5 workshops and challenge in CVPR, CCV, ICCV. Since 2020, we start to publish on this data. The data is captured, and we start to just annotating it. 6 papers published, including 2 in this CVPR. So it's a 4 CVPR paper, 1 TPAMI, 1 IRAS. And since 2022, when we moved the dataset server from Stanford to Monash, we have about 500 JRDB users from 300 academic institute and industry, including top institute from US and Europe and Asia and Australia. And not only the academic institute, but also the industry using this data. We can just keep track of that using the request and sign up and download of the data. So that's kind of what we started, why we started this data, and what was the main motivation behind that was kind of we need a new for a human-centric multimodal and robotic data set and benchmark. That's why we started to say, okay, do we have in the community beyond the self-driving cars any robotic data set, which is the multimodal and the focus more rather than driving on human and can capture like a social aspect of the human, social motion, activity, and behavior, and how it's interacting with the physical and objects and other part of the environment. And on that time, we just find out there is a clear gap in the community, and in the longer term, we need such that data to better study human for the longer term. And that was the main motivation we start this data set. With this motivation, we start capturing this data using a social mobile manipulator robot. Is called Jackrabbit, which is the customized design robot from the Stanford Vision Learning Lab, which equipped with lots of modern sensor, including different camera, like a stereo camera, RGBD, 360, 3D LiDAR, GPS, IMU, and microphone. So the data set we capture include all of those modalities, and how this data look like because of the size of the robot look like a kit. It has a very different perspective to the world. It's like look like it's a panoramic view more than what the human see, but also is like how the human see, like a child see the world. So it might be very different domain from the, again, autonomous driving, not only from the environment, but from the perspective as well. And the robot, of course, has an ego motion sensor, can move and can capture this information. And because we have the combination of the 2D and 3D sensor, it potentially is a very useful data for lots of the 3D vision problem, because we have monocular camera depths and stereo and depths and the information between them. Of course, the main motivation to capture this data is to not only consider outdoor, like self-driving car on a street, but outdoor close to the human, pedestrian area, indoor close to the human, and try to capture both domain, not rather one domain, and start to have the environment which naturally could be empty or crowded. And as I mentioned, we kind of, when we capture this data from the entire of the Stanford campus, which is including many residential area, lots of like indoor buildings, lots of outdoor buildings. We do not really plan any scenario. So there are sequences could include few people or could be very crowded, like a 200 person in the one scene. And the data set, because it's not designed, is captured, it would be include the natural biases and data set distribution we see in the daily life of how the human in the like a city like campus like a Stanford, how the people live, and what we observe there is typically what the biases exist in that data set. With this data set, in the past, actually, we did the 3 phases of the annotation, and for each one, we can publish different paper, but we start to provide 2D, 3D human bounding boxes and tracks, and also 2D body skeleton pose, and also the human action. As you can see, there is an action attribute, and then there is a human moving in this environment with these balls, which represent per frame action of what they do. But in addition to that, we introduced the concept of the social grouping, which try to cluster the people based on their correlation, how they are interacting and how they are working together. The people in the environment is partitioned into the set of the cluster. And the concept of social grouping means if there is a cluster of people, at least 2 people between these 2 has some type of interaction, right? You can just see it's like a connected component. So in the past, we just provide this type of annotation, but that's if you are interested, I think there are, the paper on those is already available to read. But what I want to focus on this workshop is what we recently started, and some of these projects is already published, some is in the progress. Sorry, just before, a part of this is not visible. Is it because a screen? Oh, okay, thank you.
Yeah.
Yes. Oh, again disconnected.
The cable here. Maybe gentle with the.
Yes. These three new annotations include panoptic segmentation tracking, which would be the one of the topics, and social group dynamic context and aim. And there is a one work which is under progress, is creating the 3D human body pose and mesh for this type of data we capture. Starting from the GRDB PanoTrack, which is a paper, this CVPR, means the data set is released, is provided, and all the code is available. And if you're interested to know more, you can join us in the poster session on Friday. But what is the GRDB PanoTrack is to provide the panoptic segmentation for the 2D images of all the pixel, which panoptic segmentation, as Laura explained, means that you provide the semantic information for all the pixel, and for the instance, you have the instance ID. But the data set is not only panoptic segmentation, it's panoptic tracking. What does it mean? It means every object has the unique ID over the time. Means if you see a bag, you don't know it's a bag, it also has an ID. If you see the cob also has an ID. And that's a definition of the panoptic segmentation and tracking. So how we annotate this, definitely it's a substantial amount of the work, and we also did not know how many category of the object we can discover in this environment, which is indoor and outdoor. So we started to provide a very clear instruction to the annotators. We provide them a list, but also give them option to add to the list. In that way, we have an unlimited list of the classes, which the annotator can decide and annotate. And at the end of the annotation, we can start grouping them and create what is actually exists in the environment. And another protocol we had is we try to annotate because of the perspective view of these images. There could be objects very far hard to recognize by human. So what we start to provide is clearly like a instruction for the annotator, just annotate if the object is bigger than certain amount of threshold, which is a 30 by 30 pixel. And also, we have a special class labeling different from the existing one. Where what aspect we find out is very important in the concept of the robotics is not like annotating the glass and what is behind the glass. So this data is contain semantic segmentation. For some pixel, we have two labels. It could be belong to the class and what is behind the class, which make it a new kind of challenge for the community and is very important for the robotic. And also floor for us is not a staff class, is a thing, because the different floor means different things for the robotics. So we are differentiating the floor based on their ID. So they are the thing class as well. And to ensure the good quality of annotation, we end up to do the different level of the quality control with the multiple run with a big pool of the people. With this annotation, we end up to have around the 72 classes in this data set, and as you can see, this data set based on the distribution, the train and test set is, as is expected, is the long tail distribution. So you have the classes, which is very frequent, and the classes is less happening. And having this, we start to kind of create split the data to the two parts. The closed word part, which is usually most frequent classes, and open world part, which is in the long tail. And we have the concept of the classes, which exist unknown in the train set, but is visible. And we have the classes which exist in the test set, which you never seen at all. And with this motivation, we just create a new set of benchmark. But more about this data set. This data set, because of the nature of the data set, is long sequences. We have a very temporary long tracklets, up to the 2 minutes of the tracking, consistent tracking. And due to the perspective of being the panoramic, we have a lot of objects, including we might have on average 270 tracklets in the one sequence. And based on how mask has a variation in size, because we have a perspective, we have quite different size of the object from the different distance. So the distribution of the mask quite balanced between a small mask, medium mask, and the large. Okay, with this data, so we start to create 4 benchmark. Is a closed word panoptic segmentation, open word panoptic segmentation, closed word panoptic tracking, and open word panoptic tracking. And we use and adopt the popular metrics like panoptic quality for segmentation or panoptic tracking quality. But also what we find out, some of these metrics, first, it do not capture all the things we need. For example, if the track is truncated, those metrics cannot capture it. And if we have a multiple label, we cannot deal with that. So there are some problem and limitation in the current metric. To address that, we also introduce a metric which is not devised by us, is the extension of the Earth mover distance to the more complex settings. Is called the optimal sub-pattern assignment metric, and we customize it and bring it for the task of the panoptic tracking and panoptic segmentation. So the high-level idea is the segmentation and tracking. You are trying to have a metric to compare 2 set of instances. Either is the instance of box, instance of mask, or instance of the tracks. So we use and adopt this metric, and then as a part of our benchmark. And using this benchmark, we start to evaluate the state-of-the-art method on panoptic segmentation and tracking in these 4 benchmark, is a closed word and open word. The way we evaluate the tracking, we use the segmentation from the closed word or open word, and then we combine it with the state-of-the-art tracking like a OC sort, byte track, and both sort. Generally, the observation was those method is kind of able to perform, but due to the complexity of the perspective and variation in mask and the number of the classes, they are a slightly struggle to deal with this problem. And definitely that seek the community to kind of a bit go beyond the COCO data set and those conventional image for panoptic segmentation and try things in what it happens in the real world and from the perspective of self-driving car or robotic, which you might have a different variation of the sizes. That's a kind of the takeaway message from this our result. Okay, how the segmentation look like and how data look like. This is the one instance of the video we created to show we kind of have this panoptic segmentation and tracking. And as you can see, every human, every bag, every object which is accountable has a consistent ID across all the video frame. And you can see glasses is also annotated, and what is behind the glass also is annotated here. Esters is recognized for many robotic tasks. Is important to know, for example, robot cannot go to the ester area. And due to also the intrinsic calibration we have between the image and point cloud, we can create a pseudo label for the 3D. We don't call it label, ground truth label, because that's definitely subject to inspection and cleaning, but definitely has a very valuable information for using and understanding the geometry and how the object and target move respect to each other. So that's exactly what I'm heading to, because we have this intrinsic relationship, we have the sense of how the object and human and object moving in 3D respect to each other in the context of open world. So this not only good for perception, I want to say, like, we are able to use this type of annotation for geometry reasoning. What is the closer to the camera respect to the other one, how the object are positioned and how they are evolving over the time respect to each other. The second work I'm introducing is the GRDV social, and this work also is accepted in this CVPR, and the data set is released and model is available. And if you are interested to know more, I will present this work on the Friday morning. Far from the scene, in this part, we try to capture more complexity of the human social behavior and understanding of that and create the annotation which is useful beyond just detecting the human and individual action. So this GRDV, in addition to have a skeleton pose and action and social grouping, now have 3 other level of the annotation. Additionally, like in the individual level, we also try to provide information like age, gender, race for every individual. And in the intra-group level, we try to model fine-grained frame level behavior of the interaction happens between every 2 humans. So that could be multi-level, means between 2 humans, they might be talking to each other, and at the same time, they might shaking a hand together. So we did this new annotation, or standing together, or looking to a robot together. So with this new annotation, we start to provide not only what's the group together and how they are interacting within a group with each other. And in addition to that, for the entire of the group, we start to provide some other information, like how body position of the entire of the group is in respect to the content. For example, in this case, is these people are standing on the walk side. Or what salient object they have close. For example, a group of people are next to the lift or next to the stairs, or I don't know, in this case, near the scooters. What is the salient object with respect to that group? And what's the group aim? What they try to do beyond the atomic action? And what's the venue, outdoor area, okay? With having this type of annotation, we start not only provide this, is the more structured description for each group as a sentence. So now with this annotation, we can just put it into the template and describe a group in the as this textual description. For example, in this case, we can see we can for free provide this description that there is 2 individuals, and we know what their race and gender is, and we know what action they do, are walking, and we know what object they are interacting, for example, walking on the floor, and where they are, and what's their aim here in this case. So this is how the data look like, which you can see the interaction between every pair of the human annotated in the fine grain. And we also provide a full description for every group, including the individual here as a textual description. So with this data, we start to, with the hype of the vision language model and their claim to be able to do very complex reasoning, we would like to know how they are able to do capture this aspect of the reasoning, human to human aspect, okay? How they can understand the human, and start to run some experiment. Due to lack of time, I have to a bit move fast, but we are using the videos and a specific prompt, for example, for a specific people by cropping the video around that person, and I start to feed it to the video language model, like a video llama or those type of things. I start to ask, can you find out what's the gender, age, or race of it? Or can you, between these 2 people, can you find out what type of interaction happening? Or can you tell me in this group what the aim of this group is? So I start to a bit see how we are good to understand social aspect of human, how these VLMs can do that, because they are claimed to be foundation model and be able to do reasoning. And we also feed the entire of the video and not ask okay, how many, we are start asking how many women you see, how many this race you see in this video, or what type of interaction you see from the list, predefined list. The only VLM need to pick one of them. And what we start to observe by running this experiment, first, these models are not performing similar. Some of them are slightly better than the other. But one of the completely obvious trend is as you go from the individual level toward more complex pair, like a relation level, like a intergroup level or social group level, the model is significantly struggle to understand. So they might be good to understand gender and age, but as long as you are trying to model the interaction or aim of the group or what type of, I don't know, salient object is next to the group, they start to struggle. And that tells us exactly, perhaps the model we are claiming to be able to understand is maybe good for the low-level perception, especially around the human. So perhaps it's a better design of this reasoning framework rather than being end-to-end VLMs is a compositional reasoning with the specialized module around the human might be way to go. And also maybe is the problem is we don't have many human crowded environment to train the models, right? Means, and that's why they can't really understand human, and maybe create a specialized foundation model trained on the large scale human crowded could be helpful. And with this annotation, we can also start creating some VQA and visual grounding because we have now can specifically ask, can you find a lady which is in a group of 3? What we are doing next is to also try to provide the body mesh for every individual, which is this work is progress. I just skipped that one. And I want to just state this one as a last slide is what we are heading toward is to having this many annotation about scene, human, object, human and object, which we are annotating now. We can create a very complex visual grounding and visual question answering pipeline, which just the engine read the JSON file we have and start to create the different complex level of, for example, I provide one example. In this case, if we want to just locate a woman, it looks like you are doing the grounding in the low level perception. But if you're asking, locate or track a woman who is walking alone, it would be need to understand the social aspect of it, walking alone or walking as a group or walking as a group of 3, carrying the bag or moving towards some object. So with the new annotation we have on GRDB, we are able to create such a grounding module. And as a summary, this is the kind of the picture I would like to provide is what we are doing with GRDB. We have a visual perception and reasoning robotic data set. We try to provide enough annotation for the community to be able to do general scene understanding, 3D vision, understand the human in the perception and the reasoning level. While this data is quite great, the only limitation we believe we have is the size. This is not the useful data for training the foundation model, but rather challenge and find out the current gap we have to understand human interaction with the object human to human interaction and the higher level reasoning module. Yep, I would like to thank the previous team members which help us to collect the data and the current team members which help us to go through this number of the annotation and provide the high quality annotation. With this, I would like to answer any question if you have. Yep.
Thanks a lot for the presentation and the enormous fantastic work. 2 questions. First, you know that there are problems about privacy of the person, so probably we couldn't use a lot of this data, at least in Europe, because of the viability of the individual recognition. So you don't have any information about who are the persons, so you didn't collect the acceptance of that.
Okay, how we collect the data, maybe that's I would like to add. First, we limit ourselves to the Stanford campus, and we try to strictly follow the Stanford protocol for capturing. Means Stanford already had this concern. But the way we just could do is this, informing the crowd, we are capturing and we will use it and how we are using it. There was the sign explaining before they come to the scene, okay? That's the only thing, maybe looks a bit unnatural, but that's way before. So we try to kind of get, unless we are anyone objecting it, we stop. So we kind of is a data which we get the permission from the crowd, it exists, does not have any privacy issue or do not raise any privacy issue. But going beyond the Stanford, like shopping center, might not be that much easy. That's why it's like we just limit ourselves to the data we captured.
Yeah. But the data set we collected together with the
Multi-view, yes, I know that.
The dean of the university asked them to close this, to close the data set because it was an identification of the fixes, even if it was in the campus of the university.
Even if you got the permission from?
This is actually I do not present from the just
I see.
The annotation and in tracking on that. So this is something that we already
Exactly following. I know the rule in the more challenge we wanted to move to the Laura wanted to move to NVIDIA has the same problem, because if you get the permission, they allow, at least NVIDIA was like, if we have like a clear protocol and we ensure everyone knows this is captured, then fine. But we couldn't really move, she couldn't move it actually to NVIDIA due to the same privacy reason. And more challenge suffer from the same problem. Yeah.
the annotation of the textual data. So probably I didn't understood well. Very interesting indeed. So you use for the annotation the VLM, assuming that this is good.
No. We are evaluating those. Okay, let me, if I explain it, for every human, we have action already, right? Means this is annotated. We have just some atomic labels, right? What is the gender? What's the age? What's the race? What the action they do, right? What's the pairwise interaction they do? And what's the group? These are predefined labels. The user go and they say, okay, I see this group. For example, the aim is excursion. Select from the very predefined rule, and we follow the same protocol. The annotator can add to the list if they want. Okay, so it's a more of the labeling, multi-labeling to the individual level, pairwise level, and the graph level, right? And that's what we did. Okay, so this one is not textual, but we have a hard-coded text which try to describe a sentence, which is a number of individuals, including their gender, age, race. They are doing this kind of action in this position. And so to describe it, we use this hard code that we just replace it with the information we have. Yeah, so it very specifically now is defined like we just place this red or green area from the atomic labels we have, and we create text. We use this information to start evaluating VLM's model, how they are performing. Now, we would like to know if they are able to understand some aspect of it, gender, age, race, location, how they do, right? And the VLM's only used for evaluation, but otherwise everything is done manually. Yep. Yes.
Annotation or segmentation.
Yep.
Yeah, as we know, the segment masking is hard to annotate. So how did you precisely and fast to annotate for each concept?
I think it was not easy and fast, and there are a lot of money spent because we have pool of annotators and lots of quality assessment from the team. That's a simple answer. One of the things we care about is not actually when we start annotating, SAM start to appear, and immediately we start to run SAM to see can we make things faster, and we end up to find out no. It's while it looks good, but it looks like very difficult to get the perfect mask. Okay, because you need to do a lot of things, and we start instead of like creating such a things which manual correction is difficult. We start to first get the good money, spend it for the pool of the annotators to give initial annotation and go through the round of the quality assessment with all the teams we have. And they start to instruct them. And again, if need a correction, we go multiple run, spend, I think, tremendous amount, like around 100K of the funding to make this annotation. And it's a quite manual process to ensure the quality. Yeah.
Did you use some model to get this?
No, we didn't, right?
We tried before, like the night that SAM was released, like 2 hours later, I used the biggest SAM model to run it on this data set to see how the quality of the mask, how would it be. And it was the segmentation, the time it takes to fix the prediction of SAMs is longer than the time that you to manually go and label it yourself. So yeah, we try several models. We even try to like label a few samples and overfit a segmentation model on that. And yeah, the result that the prediction is still a prediction, cannot be called true. Yeah.
One of the things that segmentation is not every frame, is every second, right? And we wanted to do every second and then see if we can this is a perfect quality and then maybe use the big models and then training on this and overfitting, we can generate in between. The answer is no, very difficult. Yeah, yeah.
The second question, I saw there are microphone in your robot, in the robot, and do you plan to collect the data in the future with sound that enable filtering or modeling or the sounds localization?
Capturing data or capturing from the current data provide you localization information?
Yeah, a collection of data with sound by microphone.
Sorry, I didn't get it.
Sound.
Oh, sounds. Yeah. We have microphone already in that. Actually, in the ROSBAC files, we find out the computer vision community who don't work with the ROSBAC. And we have a plan release and reformat it and synchronize it, provide you to microphone is captured. But generally, it's a crowd scene. Potentially, it's a very challenging sound you have because potentially you hear more crowd in most of the cases than what you observe. So how the microphone would be useful for social aspect, we didn't really investigate that part, okay? But the data is there. We haven't looked into that. So there's a GPS, IMU, other information provided, which we can run like a localization model, generate create a map from that. That's one of the plan we have and releasing the data. But how community use this combination of the data, like a ego motion, and then along with what we provided, I think we'll leave it to the community to decide. Yeah.
Okay.
Yeah. Thank you. Yep.
What is more detail about the challenges that you faced when using SAM for your first attempts?
It just by looking at it, it's not the quality that we want.
Yeah.
As you can see it in the image over there, that you can see we want to label even the people behind the glass. Like behind the wall, the glass wall over there, we want to label it as well. We want to label very detailed things, even and those things like sometimes very detailed. Like it label every tile on the floor,
Yeah.
but we want to label the floor as a home floor, and this make more semantically meaningful. Yeah, so
is it over segment?
Yeah, over
and also missing the critical part, like a human, the head is not suddenly right. But then and some areas doesn't have a label, doesn't guarantee every region have a label, and then we start to a bit try manually to see if we correct it and find out it takes more time correction. Okay, because there is some tools we can easily derive the contour and do that. Yeah.
Yeah, so very impressive data set. So
Thank you.
but I wonder when you train some like detection model, attribute classifier models on this data, how likely is some training model can be generalized to predict it?
Okay, I explained like this data set is not designed for you guys to do foundation model. Okay.
That's not by some YouTube video, some camera and other.
We did some study at least to try train on this and then fine tune on the Cocoa data set and test it on Cocoa to see if you just train on Cocoa and test it, and you gain some quite good advantage by pre-training. So the data has some definitely good knowledge which can be transferred to the other domain, but definitely is a one camera, one type of the camera. So so model definitely, if it's trained on that, is more likely to have tendency to perform in this view. Our main intuition is we kind of want to start evaluating foundation model or those who claim generalize actually on this data to see if that's true. Go beyond the Cocoa, go beyond the data we have, and then start challenging them exactly how they're performing. We just wanted to show the gap more than really help guys to use this data to generate foundation model. And using this data combined with this give the benefit. Yes, sure. Yeah. All right. If there's no any other question, we have a quick coffee break, right? And poster session. I don't know, poster should be upstairs, right?
Yeah.
Yep. I leave it to to explain. Yep.
So I think in the next 20 minutes, because we are running out of time. So this workshop has out of all of the submission, we have 7 papers accepted, and from different university and institutions. So out of these 7 accepted paper, this paper, Human Farmer, Human-Centric Prompting Multimodal Perception Transformer for Preferring Crowd Detections. This is again the best paper award of our workshop. So this paper proposed a novel human-centric prompting detection method to address the fine-grained multimodal alignments, and it makes significant advancement in the autonomous robot navigation. So please, one author of the paper, please come join us on the stage, and so Hamid can hand you the best paper certificate. So another round of applause. So.
Okay, I will stand for all the authors to receive the best paper award.
Yes,
And
congratulations.
thank for the authors to provide the opportunity to show our work. Thank you.
Congratulations.
Okay, thank you.
Okay, now go to let's have a poster session, and also have a break.
Not 10 minutes. We
we
extended more.
let's go until 3:20.
20.
Yep, 3:20. All right, see you guys then. 3:20.
Yeah, so that's yeah, if you want, I can send you the of this one.
Yeah, I know something gonna happen.
Yep. But you have someone that is connected online Zoom?
Yeah, but I disable them all. Like now only the host can share, and after that I can give you the host access, and you can share the screen. Yeah.
Okay, I can do
Okay.
that.
Battery?
Yeah, enough battery because I forgot to mention everything.
I have the charger for you as well.
I can go to this. No.
Yes.
So see you later.
Right.
Sorry, this is, I was confused. I thought it was gonna be a big break.
I did, I see you, hi.
Hey.
Okay,
Okay, see you. Cheers.
yes.
Yeah, yeah. No, I mean, because I was an urban for many years. I definitely spent a lot of time. Oh, yeah. LA. Maybe not so much in these sort of, I've always
so jealous. You said something.
Yeah, you should come to visit.
I love it.
Yeah, let me know you do so. Do you have still family?
I know we have like now it's like 10 years. There's some little friends that are in the area that's been a while.
Yeah, yeah.
But
Well,
I
I'm
love
supposed to you.
That's good weather.
It is. I mean, I miss it, especially coming to Pittsburgh. Pittsburgh is very gray. It's almost as gray as Seattle. So, especially in the winter months, I feel like it's kind of hard. Like after.
Yeah, winter in.
Now is the best season.
Yes, in summer, but then, yeah. What I've found is that after January, after New Year's, it's just gray. It gets dark quickly. You don't want to be outside. You kind of have to wait till spring and then things get nicer. But there's a few months there where it's all, I miss the good old California sunshine.
Yeah, like 2 days ago, I get off the airplane, there rain, I saw, oh, I didn't see rain for 3 months. Where the rain come from?
Fantastic.
But what are you up to these days? You full-time come back to Seattle?
Yes,
Or you
yeah.
want to have some new adventure?
I've just.
Another startup.
I'm still like recovering from all of that. It was, yeah, no, sort of back full time, and then it's been fun sort of research wise. It was kind of hectic, just finding funding, because they were funding a lot of the lab. So when they went under, I realized I kind of moved the lab a little too big, because I had funding rich. And so now, it's probably bigger than I want to be, but I have all these mouths to feed. So I've just been relentlessly asking everyone for money for the past 2 years. It's been, I'm exhausted of that. I don't want to have this big a lot of But no, but I mean, intellectually wise, it was fun. Like now I'm doing a lot of sort of 3D and construction kind of stuff.
So we can bring some lessons, some also cover from the startup.
Definitely, yeah. It's changed the way I think about vision.
I think even what you presented looked like to me is a kind of your vision for the how to solve the
Yeah,
perception in the driving car, bring here.
yes.
Just because look like the well thought in the sense of practical perspective rather than just research, right?
Yeah, yeah. I sort of had planned, if it was still functioning, I sort of had plans for, this is the way I would try to track it.
Yeah.
Yeah, no, so, but, I am spending a little bit of time in, Boston Dynamics. There's an AI institute in Boston. For some reason, there's a large senior connection to Jessica Hodges. Who's sort of vice president there. There's a lot of faculty there spending so much time. So it's been fun. I've been learning about lighting robots, which I know nothing about. But it's been, yeah, fun.
Perfect. Will they also be running mobile robots?
Yes. Yeah. So of course, they have like the spots and then. Yes. Oh, sure.
Okay, thank you. Okay, see you later.
What are you up to these days? I saw, so you do sort of driving stuff.
Yeah, I did
Super cool.
driving simulator and Metaphor. Try to keep it open source.
That's awesome. Where did you build this recently or?
Yeah, for the myself like infrastructure grant. Build this ecosystem for this. So it's not
What's that?
So it's called a Meta Drive. It's a new driving simulator. So like yesterday the workshop on driving, so I give a short call. Yeah, just to try to build an open source simulator. People can use and also load different real world data from other birds and using Waymo. So there will be a unified data form people can use and replace.
Cool. Is it the simulator or is it, I didn't get it. Okay, can you?
Yeah, what is
Okay,
it?
is it the also you simulate the?
It's more like we can load this trajectory into our data set and play this trajectory. So if this EU agent has some interaction with traffic vehicles, so this new traffic vehicle can be taken over by some new-based control. Basically, we can be reactive to the road.
So I guess there's sort of the view plan.
Yeah, new plan. And they are also trajectories. They are more like the offline data. We try to make this offline data more to can use this for image learning, also reinforcement. But just so I follow, can you think about, how should I think about meta drive or meta drive in relation to new plans? So I'm familiar with new plans, I'm not familiar with that.
Yeah,
Should I think about it as it's sort of similar, or is there?
it's similar, but we provide the visual renderings.
Ah.
We can provide the LiDAR depths or that being render from the first view.
Re-render, as in, so it's not like a nerf movie synthesis, but it's sort of replay the original.
Yeah, replay. That you have the, it's more intuitive, just looking at down, than just looking at down, top down view. Sure. So it provides the first point of view. Like we have a news paper last year for the scenario net that tried to collect the large scale scenario data. So people can use this data for many different situations, simulate the applications. Just recently we start building this sidewalk simulation. So today I will talk about a new simulator we built on top of MetaDrive for the Meta Urban. Allow people to simulate pedestrian behaviors, but people crowded environment, and also we can place many delivery bots or this kind of humanoid robot or lab robot inside and study these interactions.
One thing I just I think this simulated data is quite useful, but except in the area of the human, beyond the motion, right? Means human simulating human. We need social scientists and lots of means. It's very complex than really only motion. We definitely can do those things, right? I mean, we can do motion of the human, maybe. But if we are trying to kind of model very complex social behavior, we can't unless the graphics guy sit with the social and human scientists, and then they end up to model social behavior. Like even I'm trying to say like how complex human will be. About simple emotion. I can laugh at you, but I'm nervous because I shake my foot. Okay, means this kind. I'm trying to just provide the example of like a human as in like, so we don't know human as well as we know our environment.
Yeah,
okay.
So it also depends on maturity level.
Yes, that's what I'm trying to. We can do in the low level, right? Definitely, maybe for more behavior for this safety driving.
Yeah,
of course. Perhaps it might be some cases.
Yeah, like
complex than that.
locomotion.
It could be also some unpredicted behavior of the human can cause some safety issue, right? Which we don't really can simulate. That's but potentially the safer in those applications than generally understanding human in the complex level.
Yeah,
Yeah. So, and because we don't have a data on human, we don't know what exactly look like. Generally, that means we, as a computer vision, we generate a lot of 2D, 3D data, but we have less real data on crowded human. So, just if we know, maybe we can discover some, then we can simulate better.
Procedure. I agree. I actually feel like that's, I'm sorry, Mr. Talk, but I feel like that's the coolest, like the kind of natural social data. In Jack Robot, like sort of seeing people mill around.
So it doesn't have that much potential because it's a people of your daily life, right? I mean, it's not that big to get all aspects of it. We're trying to approach people, interact with them. I just find with ego also. Ego killing means we can capture ego for those type of things, like social aspect, wearable process. But usually they are really kind of capturing the one, like if there's one other human maybe in the environment and privacy issues, right?
Yeah, by the way, yeah, this is a mother job simulator. We can load different data into our simulator and provide a render. We can also provide some 3D for this projectors. Many data set just projectors, and we can provide this view. Yes, build on top of this right? So just have try to make this simulator efficient and flexible. People can see some top of that. With defined results, now reject 3 times, then throw to keep on making get a self.
I mean, I'm actually super impressed you got NSF on because I would have thought. I always get the sense that people are like, oh, self-driving, and then like I always get people saying, oh, industry should fund this. So
I try to teach this more like bridge for the industry and academia. The industry have a lot of data.
email don't have such data infrastructure. And when you do have an ecosystem, a plan for all people to control the industry.
Generally, like you know that what's the market of the means the aim for really doing the autonomous driving is seems to be never achievable like the highest level, right? Means then the companies start to be like I'm trying to understand exactly what we are standing in this self. How means company do everything for benefit. Means if there was a time which everyone care about self-driving because they was hope, which we can make it. But at least they know they can create safety and then, but not, I don't know, it's called level 5 or yeah, highest level seems to be not achievable. That Tesla tried to claim multiple times. What is exactly the state on that? Means how much industry investing? What is the goal, realistic goal to reach in the sense of like autonomy and self-driving? And is there more funding? Like what? Because if there is no benefit, they don't do it. And what is what they want to reach? And then
Yeah, my sense is it's actually kind of like an economics question. So, okay, the reason why the math doesn't quite make sense to me is that typical companies like Cruise and maintaining its fleet of cars, it's enormously expensive. It's about they burn over $1 billion a year. So it's a crazy burn rate where you don't see a profit. Like the question to me isn't enough. Like you can get it to work in very constrained scenarios. Like there are Waymo's operating in Phoenix and certain routes, but no one is making a profit.
yes,
And so
that's what I'm trying to say. Company they don't get profits, they don't.
So that to me is a real question. It's not even that sort of like when it gets big enough where you get a return for the $1 billion you're spending every year. But I do think that kind of uniquely Tesla is full self-driving. You can argue that it's ingenuous to market research. That there is a consumer market for it that actually pays for its own research. Because people buy that. Yeah, they sell cars and they sort of buy that functionality.
But that's not, it means they are not, they want the safety, it means they are able to, means we cannot have a driver not looking, right? That level, which means this seems to be not achievable because of many also economical reason, right? Means you just need the one few crash of that due to some control safety, whatever, which the company goes off completely. It's like an air crash completely for the company. They don't do that, right? We don't, it's a risk for them unless they are sure the percentage is too tiny, which they don't risk it, right? The one they are targeting is not definitely that level, right? That currently even Tesla should not really target the like a the one which you can just no driver exists, no one look at the window, the car itself drive it.
I mean, I think that they're still working toward it. So one of the lessons I took away from sort of, as far as I can tell, it's true of all robotics, where it's not good enough to have an answer. In the sense of, one reaction is you would say, leave me alone for 2 years, let me just work on it. I'll come back with a solution. And robotics never works that way because it's such this endless like system. So it almost seems like as in addition to the difficulty of solving a task, you need to have a flight plan to get there. Like somehow there has to be a pathway. And then sometimes that might be just as hard as solving the problem. Like how do you sort of incrementally.
But for us as an academic to solve this problem, it's very different for them to solve the problem, right? It means we are talking about the very good robot system, maybe X number, but for them is even like a 99.9 is not percentage of accuracy is not yet because the profit, the risk of that, that's what I'm trying to say. If the industry would be our researchers can continue like any other area to do that, but is that industry yet put money for the research of that or not? That's my question. Is it like a
You're saying is industry still putting money? You're asking.
yes.
I mean, well, like Tesla is and Waymo, like it feels like there's a consolidation. So
Interesting to know. More or less look like it's just dead end for them. Yeah,
We're in the water research team.
yeah.
Research. It's the publisher has to solve these corner cases.
Yeah.
Rather than publishers.
Yeah. And in the morning, like I don't know, it happens in any other workshop or not. Like we kind of get attacked why the Zoom, right?
Oh, really?
It's put in irrelevant content to keep disturbing us. Means that Zoom, that's what I don't know why they organize, but Zoom should go through the virtual platform.
Yeah.
Yeah, but not only registered people can do that. I think we did a mistake. We didn't tweet that. Yeah.
Not that one, which I'm not problem.
Oh, that's a problem. Sure.
This morning I sent you the Zoom link.
Yeah.
Yes.
Oh, thanks.
Yeah, go to the phone, grab it. Yeah.
Oh, join Zoom, yeah. So that was email.
Email, yep.
This one?
Yeah, yeah, sure. It's unmute yourself.
Unmute.
Make them again you there.
Okay, now I'm gonna do share. Now say hide.
Should I put my volume on in case people ask questions? Or no? I'm turning that off because you better. So I'm gonna turn that, which is fine.
Oh, yeah.
Yeah, I'll let you have your volume on. You can see you can see the screen?
Yeah, you can see the screen.
Okay.
Okay, let me
Oh.
first, yep.
Sorry, 1 second. Whoa. I can do that? Oh, sorry. Okay, once I start sharing. So I'm going to go back here to Zoom. And now we'll say share desktop. And then there's a way of more disable annotation by others.
Yeah.
And then I will also hide names or hide meeting controls. Okay.
Awesome. Hey, it's my honor to introduce Professor Deva Ramanand, a distinguished professor in the Robotic Institute at Carnegie Mellon University and the former director of CMU Center for Autonomous Vehicle Research. So Professor Ramanand's expertise in computer vision and machine learning, particularly in visual recognition, he has earned numerous awards, and his pioneering work is supported by NSF, ONR, DARPA, and leading tech giants like Intel, Google, and Microsoft. He served as the CVPR and contribute to editorial board of prestigious journals. So please join me welcoming Professor Deva Ramanand.
Thank you. Okay. All right. So we have a cozy room here. Feel free to interrupt me with any questions as we kind of go through stuff. So I'll try to give a view of how I want to think about learning models for embodied cognition. And so I'll start with this perspective of so all this incredible innovation we've seen for learning word models that evidently allows incredible phenomena to emerge just by defining a next token prediction task. I want to try to do this for visual data, but in particular 3D or 4D data that captures how the world around us is structured and how it's changing over time. And so maybe we'll sort of dig into it. So kind of riffing off of the kinds of data that's available for Jackrobot, I think it's very similar to the kinds of data that is collected by an autonomous vehicle. It's multi-sensor, it's egocentric, the car moves around and collects data. And just like in the world of self-driving, anytime we have any data set, there's only a tiny fraction of that we can realistically label. So just like we see this innovation in self-supervision for word models and for images, why not try to do this for this kind of structured data? So I'll try to show you one pathway of doing this. And that is perhaps the most reasonable way of thinking about this is instead of doing next word prediction, let's do next LiDAR frame prediction. So given we train a neural network, given the past T LiDAR sweeps, we try to predict the next sweep or the next T sweeps. And of course, we just let time unfold and we actually see in reality what the next T sweeps were. And we look to find some error between the prediction and what they were. And then we use this as a loss function to learn or train this neural network. And of course, what's really nice about this setup is that no labels are required. So in fact, one more thing that I just want to call out, actually what is required is we just need the raw LiDAR sweep and we need egocentric poses. We need to be able to place these sweeps in a global coordinate frame. But what I would claim is from a self-driving perspective, this is incredibly natural. We always align to a map, and a map is a global coordinate frame. Okay. But I'll call out that there's actually, I think, a difficulty in just phrasing the problem as I suggested, and that is if you just tried to predict future points from past points, imagine a scenario where actually nothing is changing in the world. It's stationary, and this is actually a pretty good approximation for a lot of scenes in practice. But the car is moving, so the ego sensor is moving. And it's not too hard to imagine that because what you're actually seeing is the intersection of rays with geometry, it looks like points that are being sensed are moving over time. But of course they're not. The world is stationary. And I think this is a really important point. You might think that each of these points represents, oh, one of these points is a part of an object. And so if that object is not moving, then that point won't move. But that's not correct. These points are just simply intersections of rays with geometry. And so they will swim on top of a surface. And so then what I claim is that this means that if you naively just try to predict future points from past points, what you're actually going to predict is ego motion and ego intrinsics. You're not actually going to predict things about the way the world is changing. But that's exactly what we want to do. We want to learn models about how the world is structured, how the world evolves, because then we think we'll be able to move around and operate safely in there. And I think this phenomenon has shown up. I was hoping for a discussion, but maybe we could do this at the end. But this phenomenon has also shown up in a lot of benchmarks that try to evaluate flow or forecasting. And a lot of them traditionally try to evaluate flow or forecasting in an egocentric coordinate frame. And the reason why I think that's a mistake, and I wanted to, because I think Jack Rabat, the benchmark might also do this. But the reason why I wanted to try to argue that's a mistake is that if you can evaluate things in a world coordinate frame, then very quickly it becomes clear that most of the time the predicted motion for a point is trivially easy, just zero, because most of the world is static. And in fact, most papers, or a lot of papers on LiDAR flow for self-driving did not do this. They evaluated in an egocentric coordinate frame. And then what they inadvertently were really trying to predict is the motion of the car. And it turns out that once you evaluate in this world-aligned coordinate frame, like the motion prediction becomes an easy problem for 90% of the world, because 90% of the world just say zero, and that explains that point. Because that point is really not moving in 3D. And so we had this paper in WACV this past summer that just pointed out that if you were to evaluate scene flow in this world coordinate frame, it actually changes the whole landscape of what methods work and then what methods should focus on. So I want to try to argue that we should do the same thing even here in this embodied setup of robots moving around a crowded room. I guess the phrasing of it is a little strange. So I still argue that as the robot is moving, you can define a world coordinate frame at the last ego frame at time t. So you're going to take a snapshot here, and then the robot's going to do some future stuff, and then it's going to the other people are going to move around to do future stuff. But you can still sort of ask. You can still ask, how will the people move? And you should you can make predictions about that and compare it to the ground truth, but you don't have to know how the robot's going to move. And in fact, if you allow for the other option is to stick an egocentric coordinate frame, but then you provide algorithms with future knowledge of how the robot's going to move. But then that also seems a little wacky, because that also might kind of leak knowledge about how the rest of the scene is going to evolve. Because maybe if the robot goes somewhere, the person can't move there. So I actually feel like there's I think there's a clean way to think about this when you define a world coordinate frame at the ego agent at time t, and then evaluate all predictions about motion from there. So in any case, yeah. So a suggestion. And so if we lean into this kind of view, I'm going to apply the same hypothesis here. So given the past t frames, what I'm going to do is I'm going to predict not directly points of where I think LiDAR points will be in the future. I'm going to predict space-time volumes of occupancy. So I'm going to predict, I can think about this as a 4D data structure, an X, Y, Z, T, and at each voxel in that 4D, I store the number between 0 and 1. Is it empty or is it solid? And you can think about this as almost like a density that you could also, instead of storing it explicitly in this voxel grid, I could store it implicitly with a NERF. That would be the cooler thing to do these days. But we just did it like an explicit grid. But now in any case that you have some notion of volumetric occupancy, now the crucial thing is, in order to generate a future LiDAR sweep, we're going to use known sensor pose. We're going to say, I know where the car will be in the future. I even know the LiDAR beams that I'm going to shoot out, and I'll simply just raycast from those known locations, and I'll throw my rays out. And just like I would do in NERF, I will differentially render a LiDAR sweep instead of differentially rendering an image. And once I render a LiDAR sweep, I can then compare this thing to the actual LiDAR sweep that I see in the future and use this as a signal for learning. And what's kind of cool now is that by training this, what we find, and I'll show you in a second, is that volumetric models of the world emerge. We're never labeling anything about the shape of a car or how it moves, but it turns out that if you do a good job of understanding the dynamics of the world, that will allow you to do a better job of rendering LiDAR sweeps. And importantly, this thing can be trained sort of at scale without any labels. Okay, so I want to sort of contrast this. This was a paper at CVPR last year. Contrast this with like other methods for point forecasting. So SPFnet and S2Net are, let's say, traditional methods that just try to predict future points using oftentimes encoded in a range image or in a point cloud given past points. And let's say we can a very reasonable way is you can compare the distance between the measured points and the actual ground truth future points. And let's say these networks have an average of 4 meters of error, L1 distance. The first thing we said is, okay, if we really buy this kind of 3D world coordinate frame reasoning, let's define a super trivial baseline, which is I'm just going to aggregate all my points I've observed over the past T frames, put them in a voxel grid, a binary voxel grid 1 and 0. And now I'm going to do the same thing with known future locations of where the car will be. Let me shoot out rays and intersect this binary voxel grid. So this baseline requires 0 learning, but it turns out this actually produces like half the error of state of the art, because these other methods don't really enforce the rigid structure of the world, and just sort of simply by trivially doing it, you can already do way better. And the reason why it's so effective is because remember, once again, like most of the world is static. So if you just encode that, you'll do a look around this room, there's not a lot of dynamics here. But then if you do what we're doing is actually train a network to predict a volume, and then you actually raycast into that volume to render a sweep, you can do much better. In particular, the volume will capture dynamic objects that are moving over time. And you can almost roughly half the error again. So I should say that we've sort of been pushing this direction pretty aggressively. Wabi has a really nice sort of follow-up work. And we've been running a benchmark competition. So what's nice about this is you can do this, you can train this thing at scale, you can also evaluate it at scale. You don't need any ground truth data. But this is almost the way that we almost thought about this is kind of you can use point clouds and rays as kind of this cute scalable way of evaluating 4D occupancy modeling, which is kind of a hard thing to collect data for, but it's easy to collect LiDAR sweeps. And some kind of fun things you can do with this is that now that you have this emergent 4D model, remember again, the way that we obtain these LiDAR sweeps is by throwing out rays from some known locations. And what we can do is we can say, well, what happens if instead of throwing out 32 beams, I can throw out 16 beams? And what happens if instead of throwing out 16 beams that are mounted at 3 meters above the ground, what happens if I do 16 beams mounted on a large truck? And so you could synthesize what the world would look like from different LiDAR platforms. And as far as I know, this is the first time. Usually in the world of 3D processing, people might not know this, but it turns out that it's very rare to be able to train on one LiDAR rig and test on another. That's not true for images. You can train on a Canon and test on a Nikon. Like that's quite readily doable. But for LiDAR sweeps, because of the LiDAR patterns, it's very hard to generalize across. But this almost becomes trivial once you start modeling the world as a 4D entity. And I like this phrase down below, the picture of Judea Pearl. If you guys know, he was kind of the author of Causality, and he had the statement that always stuck with me. He said we should make a commitment to model the world and not the data. And I think about that as this distinction where the world by itself is undeniably 3D and dynamic. It's 4D. The data that we see is a combination of having sensors that sense the world. But if you distinguish those two, what's kind of powerful about that is I can throw in different sensors. Maybe the most useful thing about this is this should allow you to train across different sensors using a single representation. And as we know that typically, training with more scale and more data is a good thing. And maybe having diverse platforms also is a good thing. So we showed some examples of using this to help plan. If I have a guess about where things will be in the future, I can safely try to get to a target goal without hitting stuff by evaluating different trajectories. Let me skip this for the moment. And now I wanted to take sort of another aggressive view of on this, which is instead of just trying to build up this dynamic model into a space-time volume, let me actually explicitly try to decompose the world into static components and rigid objects that are moving. What I'm showing here is a process that will just take this LiDAR point cloud on the left-hand side and produce a reconstruction on the right-hand side, which I think are pretty complete. And I'll show you a process that does this in a completely self-supervised way. It requires no manual annotation. Okay, and the insight is just we're going to build a very trivial kind of compositional model of the scene. So let's start by assuming that we have noisy estimates of ego pose, which are given by these strong colored coordinate frames, noisy estimates of bounding boxes of all the moving objects. And I'll remove this in just a second, but let's pretend we have these noisy estimates of all this. And of course, we have the actual noisy estimates of the LiDAR sweeps. And what I'm going to try to do is come up with a model of fitting a surface, a dynamic surface to all these measurements. And it's going to operate as follows. The first thing I'm going to do is, given all these dynamic annotations for moving objects, I'm going to align all the points together in a single coordinate frame. So I get like a almost densified point cloud. I can also do this for the background as well. So I'll think of the background as another object. Okay, so now I have this dense point cloud. Now, given this dense point cloud, there's a slew of surface reconstruction algorithms we could give it to. If you want to be cool, you can do an earth and a sine distance function, or you can do classic kind of graphics mesh-based reconstructions. And once we have this surface reconstruction for all of the annotated objects and for the background, I can recompose the scene with the big background surface and all these moving object surfaces. And now what I'm going to do is I'm going to take this reconstructed surface and compare it to my LiDAR measurements from all these different frames. And I can define an error, a point to surface error between these two. And now I can use this as a loss to try to optimize for better poses and better surfaces. This is essentially a reconstruction error. You can define it in terms of 2D if you want to think about, like, I can render a LiDAR sweep from here and compare it to this LiDAR sweep, or I can even do a 3D error, right? Compare the distance between all these points and the closest point on these surfaces here. So once you do this, I can show you this optimization in action. If you so this is kind of an interesting visual. The left-hand side represents the actual poses you would reconstruct if you just use off-the-shelf annotations from flagship data sets like NewScenes. If you use the provided ego poses that they give you and the provided object poses for all the ground truth, this is showing you that they're actually not that high quality poses. But if you simply apply this optimization, let me keep jittering the poses and rebuilding my surface so that I minimize my reprojection error to my LiDAR points, this is the optimization in action. And you very clearly crystallize with pretty high accuracy the background and also the object. So what this is saying is that I almost claim that in some sense, this makes a lot of sense. If you know how data is annotated, oftentimes when you annotate a cuboid on a car, you just kind of manually draw it. But it almost feels like we should do some geometric alignment to get really high precision estimates of like how the car is moving. And that's exactly what this is. You can almost imagine the argument is like, this is how you should produce annotations. Okay, but there's one important piece of the puzzle to kind of get right. And that is modeling LiDAR. I'm going to ask this kind of surprising question, which is, what is a LiDAR sweep? And even though every sweep that you've ever seen in any data set looks like this thing on the left-hand side, it looks like kind of these static points that are captured at some time interval, that's not physically at all what happens. What happens is that this is a revolving sensor. In the world of cameras, we would call this a rolling shutter. It's this continually spinning thing. And as you're moving and as the world is changing, the thing keeps grabbing measurements. And the fact that it's actually measured in this way, but we model it in this way, causes a whole bunch of errors that my claim is we can actually easily fix them if we just think about it in this reconstruction perspective. Okay, so the first problem is that What we're actually seeing here is a reprojection of all the measured points. It's an attempt to create a virtual view of if the car was at one location. It actually takes about 100 milliseconds for the LiDAR sweep to finish. And there's this question of, given all those points that I measure as I'm moving, I can try to redraw what the sweep would have looked like if I was at the beginning of those 100 milliseconds, the pose of the car, or if it was at the end. There's a choice I make. And what that means is every sweep you ever look at, there's going to be a seam in it. And all the points on one side of the seam were collected at t is equal to 0, and all the points on the other side of the seam were collected at t is equal to 100 milliseconds. They were collected at different times. So here's a case where you actually run into trouble. If your car is moving this way, I'm sorry, if the ego sensor is moving this way and the other car is moving against you, it's possible that you actually see the car twice at different time steps, and you'll actually see two people in the car. And so if you naively try to do your reconstructions and fits, you'll get totally confused. You'll think the car is too long. And actually, I think this is one reason. One thing that's always been kind of confusing to me is that there's a whole bunch of work on like reconstruction of urban, like doing NERFs on urban data. And what's always a bit surprising is a lot of times people don't use LiDAR. They'll just use RGB cameras. And I think one reason why is this. Is because this abstraction of LiDAR as a sweep screws up the reconstruction because you're actually not getting the right signal. But I'll try to convince you that there is a fairly easy way of getting the right signal. I'm going to show you another problem. So that first problem arises when you have moving objects. What was also kind of crazy to me is even if the world is not moving, things still get weird. And what happens is, let's say you're just a static scene and this is a car that's moving this way. And as the car is moving, you know, the sweep is rotating around. And then the kind of interesting part is that eventually what happens is the car can get past an occluder and see a point here. But if I try to recreate a virtual sweep over here, what's going to happen is that it looks like I'm seeing through the object. And so you'll see this with LiDAR sweeps. So it looks like there's noise. In fact, there's been a whole slew of image post-processing, like filtering hacks that try to remove this. My claim is that it's doing exactly what it should be doing if you think about this as a continuous sensor. It's not noise. It's actually measuring real honest to goodness information. And so the question is, how do we take advantage of it? How do we model it correctly? And my claim is this NERF-based view of the world when I raycast, I think fits in beautifully with LiDAR. And all I need to do is, instead of optimizing for poses of entire LiDAR sweeps, I'm going to model sectors of LiDAR sweeps, or in the extreme case, slices of LiDAR sweeps. So I'll have 360 of these, and each one of them will have its own pose, and I just optimize. In fact, it's the exact same optimization I wrote before, but we just do it at an individual slice level. Now, when you do this, what I show here is this is what happens if you trust the original pose annotations in new scenes about moving objects. This is what happens if you just optimize for the overall pose, still treating a sweep as one object. And this is the improvement that you get if you actually treat each sweep as a continuous slice, modeling the fact that it's a rolling shutter. And clearly you get like much more accurate reconstructions. And what this means is much more accurate estimates of pose and velocity. This is all the juicy stuff we want to, try to estimate and reason about for an embodied agent. So I should also mention that we have a paper on this that got rejected from this conference, but NURAD got in and they point this out as well. So they have I encourage you to go see their, I think they have a poster in a couple of days. So in my view, this is kind of a really important thing. This is one reason why it's been so hard to do proper multimodal reconstruction, because we've kind of always gotten this little bit wrong. But with all this sort of raycasting view of rendering, it's actually not that hard to get it right. Oh, and this is kind of the fun visual I wanted to show. That what we showed is you can initialize this optimization with ground truth tracks and you get better performance. This was the first visual that I showed, that you can produce better reconstructions than what new scenes gives you. That new scenes gives you the left-hand side, we can produce what's on the right-hand side. But that's, of course, starting with new scenes annotations. But what happens if you don't have any annotations for any moving objects? Well, the first thing we showed is if you have reduced frequency of annotations, it doesn't really hurt at all, because you can just still annotate with a rough guess about where you think the pose is and then, fine tune for the reconstruction error. And then what we also tried is just running an off-the-shelf detector and tracker and using that as initialization. So the hope is that what this means is we can basically do this kind of space-time dynamic optimization on unannotated LiDAR data and basically reconstruct all the moving objects and stuff that's there. And the hope is if we can do this at scale, then this would be a rich data set for I don't know, studying behavior, studying movement, studying trajectories, which we really don't have a lot of because it's so difficult to, I think, to actually produce high quality track annotations. Okay. Okay, so that was all about sort of doing space-time fitting from LiDAR. What about doing it from RGB? And so we've done quite a lot. There's a particular student, Gengshin Yang, who just graduated. But he has a slew of papers that try to address this problem of doing 4D reconstruction just from RGB video streams. And he's also gone to a lot of work to sort of produce open source code. The goal for this, we haven't done this yet, but the goal for this is to almost be the equivalent, a dynamic equivalent of NeRF Studio. But there's some groups that have started building on this code bases already, but this is machinery for trying to do reconstruction of dynamic scenes. So I sort of won't get into it here, but we have quite a bit of work of trying to do large scale reconstructions from drone footage or even city scale reconstructions of all of Pittsburgh, where we have to do sort of, we've collected data from an autonomous vehicle fleet, of course, over a year, where you have to deal with parked cars and people that are moving, and even the fact that the leaves change color. But there's actually ways of building large-scale NeRF reconstructions at the scale. I won't talk about it here, but I'm happy to talk about it offline. But that's all about building static models of the world from large-scale data. And the thing we've been really pushing is trying to also build dynamic models of a changing world. So maybe this is also more akin to Jackrobot. So this is the kinds of things you can build from just a single view, sort of egocentric captures of moving people. And also one of the things we've been pushing is trying to do more with a sort of interesting clothing. One of the, I guess, maybe unique perspectives that we've been trying to push is rather than trying to bring to bear big data, the way I'm going to reconstruct this person is by using knowledge of how I think people look. Instead, I just want to actually solve this as a differentiable rendering problem. Given a video stream, let me try to fit data. Let me fit a hypothesis to match what I see in the video stream. And actually, maybe I'll just sort of show it here. The core underlying technology for all the results I just showed is actually just very classic vision. Vision is inverse graphics. Let me hypothesize a canonical shape. Let me hypothesize a deformation that's modeled by like 20 canonical bones that can translate and rotate, and every other point in space is a linear combination of those translations and rotations. I also hypothesize a bunch of cameras. So given a canonical reconstruction, a deformation, and a camera, I can just press the render button and I get an image out. And now I compare the rendered image to the measured image, and then I use it as a loss to then optimize and re-estimate my canonical reconstruction, my deformation, and my poses. So this is almost an old school way of thinking about vision. And you might first think, okay, well, this seems terribly under constraint. There's lots of interpretations of 3D structures and deformations that would fit to this. And how do we really make this tameable? And so one question is, what is the best way of exploiting prior knowledge about the world? And typically what I claim is what we've done is a lot of approaches tend to exploit 3D priors about, I build a database of scans of 3D people, and I use that to build priors about how I think people are shaped. Instead, what we've done is essentially try to leverage 2D knowledge in terms of other kinds of reconstruction losses. So in addition to reconstructing images, we've tried to reconstruct object mass. We try to reconstruct motion flow vectors. We try to reconstruct pixel descriptors like dino descriptors, and reconstruct depth and normals. So basically, if we endow all these points, not just with a color and occupancy, but also with, let's say, dino descriptors that live in a 3D field, when we render, we can get all these predictions, and we just compare the predictions with these measured values and try to get a signal for optimization. And one of the things that was really, there's a slew of papers that Gengshin has done. And like I said, all of this has been manifested in this code base that we're trying to make easy to use. And one of the crucial things about making this work is knowing when we can trust all these other estimates. So of all these other cues and modalities, the one that we find most helpful to help reconstruct the dynamic scene is the motion. And it turns out to be super important if you're going to use off-the-shelf optical flow to be able to know where you can trust the flow and where you can't. So even so, many people might use things like RASH, but we use a homebrewed version that we developed that spits out uncertainty estimates, and that allows us to apply motion losses only on pixels that we actually trust the motion for. And in fact, the motion model we use is very graphics inspired. So this is an example of, I have 20 bones, and each bone is just literally, it's a control point that stores a translation and rotation. And then I have a linear blend skinning model. So the translation and rotation applied to any point in space is just a linear combination of these 20 canonical ones. And that way I can model deformations such as twistings of the legs or even changes of shape. And I want to show off a fun example of what you can do with commodity multimodal sensors. So I think I've kind of pushed so far an approach of just doing, space-time reconstruction from LiDAR. Now I talked about space-time reconstruction from images, but in reality, given the Jack Robot rig, we have multimodal sensors. And in fact, something that I'm always perplexed by, I don't see why I wouldn't see more of. We all have a multimodal rig in our back pocket. I have a LiDAR sensor here, and I have 3 cameras right here. So that means very easily I can take a video right now where I get multimodal data. And what's nice about this is actually, measure depth, which really helps solve this reconstruction problem. And we can try to do compositional reconstruction, just like I showed before, where in addition to having this this rigid body transformation for this cat, it can also deform. And one of the, I think, kind of cool things we can do with this is, usually with NERF, you just pick a random viewpoint and you say, oh, look, I can render this scene from this other viewpoint. Typically, you don't pick extreme viewpoints like this bird's eye view, but I think it's sort of fun to show. But I think maybe the coolest thing is if you've actually reconstructed motion of moving things in the scene, what you can do is you can put a virtual camera right in front of the cat's face, and you can look at what the cat's looking at. That's just another view synthesis problem. And in fact, you can even do something else kind of fun. You can also put a virtual camera right behind the cat, so you see the cat. And now this is because it's a video, I can animate this, and you get to see from this single video, this is the view of what the cat is seeing as it's moving around. This is kind of gnarly here because the blue camera is inside the ground, but once the cat moves, you see it actually move around. So this is a fun example of, to me, this is just analysis by synthesis. This is hypothesizing a 3D world in dynamics, rendering it, and then seeing how the renderings compare to the measurements and just backpropping. You can see fun examples of, so this is a pretty dynamic scene of someone, Andrew was playing with his dog in our office. And the bird's eye view is kind of impressive here. And you can see there's a whole bunch of areas that are white, and they basically represent parts of the scene that we've never seen in the video. So that probably is the right place to throw in prior knowledge about, even though I haven't seen that corner of the wall in this video. I kind of seen other walls before, and then I know walls are self-similar. I can probably get some good estimate of how to fill that in. But I sort of intentionally wanted to see how much can you do just by listening to the pixels, not by requiring prior knowledge, not the big data story. I think of this as the small data story. And I like this video as well. So this is Gengshen walking around. This rightmost video to me almost feels like a first-person shooter game when you're walking around. Got it. And so once again, we've tried to put all this code online and with lots of tutorials. So we hope people would be interested in building off of this. Okay. Oh, here's a recent piece of work just put online today of because we're intentionally trying to fit to the data and not bring in prior knowledge. Probably this is not going to do well compared to existing approaches when we look at humans, because humans, we have incredible amount of prior knowledge. We have simple models, we have body shape models. And so our take was, well, maybe let's try to make this super hard. Let's look at people wearing crazy clothing, where almost the clothing moves as like another body part. And so now what we've done is we've sort of glued a simple model where you have strong priors about a person with data-driven models that tries to build bones and articulated models for the particular piece of clothing in a video, and use both to model these captures. And again, this is done from a single video. Although in this case, we had to spin around the object to try to get a full 360 coverage. Right here. Yeah, and so the trick really was integrating clothing bones with human bones that we already get directly from data-driven models such as HMR. Okay. And then maybe I'll sort of conclude here. So the moral of the story was, I think if you want to see the bet that I'd like to make about if you want to see the same innovation and transformation we've seen for large language models and large image models, if you want to see it for the sort of in the robotic setting, I think we'll have to focus on 3D and 4D data. And so one of the challenges is that even though we don't have LiDAR data sets that are a lot as big as Word data sets, LiDAR is incredibly structured and we can do a lot of self-supervised fitting. And we can even model, the intricacies of LiDAR sensor patterns and combine that with camera sensor patterns to try to get high fidelity. One thing that I actually measured, one thing I didn't actually mention is that I think by actually modeling the rolling shutter of LiDAR and by modeling the rolling shutter rays even of cameras, what's kind of cool is that you essentially turn your sensor into a very high frame rate sensor. So at first you might think rolling shutter is a bug, but my argue is a feature because you essentially turn your sensor into, instead of a 100 hertz sensor, like a 10 kilohertz sensor, 10,000 hertz sensors, because you get a reading every single time instant. And that's actually super useful if you're trying to understand the space-time geometry of what's happening. And in fact, another thing that's always been difficult is that a lot of times when cameras are not co-located with LiDAR, they'll see different things, and this adds a headache about how you try to fuse information. But from this perspective, this is also a feature because now you have more views. You get to see the world from two different viewpoints, and that actually should help reconstruction, not hurt it. So I think that this kind of embracing of rays in a forward model is really helpful for doing reconstruction from these multimodal rich data sets. Yeah, which can allow for some, I think, fun applications below. So with that, I will conclude. Any questions? Yeah.
I think the great presentation. And I'm curious about for your second method to construct the object from LiDAR points. So what happens if the objects kind of deform like a picture?
Beautiful question. So we haven't done that yet. So right now, everything in that method is baked on having rigid objects. So that's kind of like the next step. So I'd love to be able to do that. I'd love to be able to, for Jackrabbit, try to actually do like deformable reconstruction. Like my guess is it's doable. Especially if you have multimodal sensors.
You're very interested topic.
Yeah, I think it'd be cool. I think it'll be kind of fun to look at. Go for it.
Well, when you say you're like increasing the frame rate of the LiDAR by just going speed, but at one point, at one instance, you only have like one heading of the data. So you have 360 degrees that you have to like actually work on. So what was that exactly better than just?
Yeah, it's this hypothesis. So here's a very concrete claim that I make, and this is totally unsubstantiated, but this is the bet I would make. Imagine I have a synthetic data set, and I can choose to render a truly global shutter LiDAR at every, 100 milliseconds, or I can choose to render a truly revolving LiDAR. I think I'll get more accurate reconstructions with the revolving shutter LiDAR because it'll be easier to interpolate. I'm kind of getting my intuition. It's kind of a more spread out sampling of the space-time volume versus a true global shutter is like I close my eyes for 100 milliseconds. Versus this is no, I keep a little sliver open. But it's a bet.
And to follow up, let's say you deploy the robot on the indoor set. That's going to be a lot more dynamic than what you have outdoor. So what kind of like changes would you expect?
Yeah, I mean, so for example, I did show like the indoor settings, but not like Jackrabbit. It was one student with his dog. So that is doable. We don't have great scaling. Like we basically have to do like a reconstruction per object. That means if you have a crowded scene of, 20 people, I think it'll be super compute heavy. And that is another downside about all of this is that this is all very compute heavy. So none of this can actually run on a robot right now. But I think the way I would think about this is I think this can be done for sort of like offline processing. But you will pay the price. Like right now, I think things will scale linearly with the number of moving objects.
Nice. I think that's the last question you could take.
Okay.
Yeah.
Thank you.
The program.
Thank you. Thanks.
Have a lot of slides of that, but because we are not a lot, so I think we can do very quickly. So my idea is that to discuss with you about two different topics we are working on. That is about the fact that now many robots can move, see around, and since this can be done by many different moving objects, now we can work a lot of things with this kind of embodied AI in two different directions. One is large-scale monitoring in urban area, as you are doing, and what's the interesting data set you are collecting. And the other one is instead in a personalized interaction at home that is share many different problems, even if the location is completely different. We are working in these two topics because of many Italian projects that now are ongoing. The first is this one that is called the ecosystem, that is about, okay, tell me something about what's happening around. For instance, where are the children if a car is coming in, or if the children are in dangerous situation or similar things, or instead inside looking, this is done also with the European project to say, okay, please robot, go around, take my bag that is in another room, do something for that. And so many of these kind of questions can be solved in similar things. So from one side, we have the goal of the system that could be given by the question or by a private goal. We have the human world, the robot world, and the physical and synthetic world. And in this work, at the end, we have do the similar things: acquisition, data processing, 3D structure understanding, and then for a robot that is reasoning and planning and possibly saying in natural interface what is doing or asking or receiving a command in natural interface. So in this environment, we are doing a lot of things. And I would like to show you just only two insights. The first is about the 3D structure of the world. So in a situation like this one, if you have a moving robot as your jackpot or similar things, the idea is how can I understand the distance of all the people and also can be used after detection and tracking or in human behavior understanding. In order to do that, we use the large data set we created and presented here in CVPR also some years ago together with Laura, and she was here before. And since we had this synthetic data set that is very large, we was able to do many different things, and in particular detect people, understand them, but also understanding the position. This is something we did in 2021 together with Laura. So starting with the ModSynth and then moved in the new, in the real scenario. And this is instead something that we finished last year. We presented here in CVPR last year. That is about the estimation of the 3D distance used for tracking. And so I don't want to spend time about this track flow system together, but just only to say that in order to create the cost matrix that take into account the previous track detection and the new detection, we use a normalizing flow, but we did also the 3D distance. So we proposed this architecture that is quite stable and robust, because we use also in practical situation, that is about the understanding and providing an estimation of the 3D distance for each detected object. So very easily, we started with detection, not a single frame, but in 5 frames, so a number of frames in order to be robust to the occlusion. And we started with all the detection that we have, that we could use also in your data set indeed. Then we created an estimation of using convolutional neural network, in particular convolutional STM, in order to take into account also the frame, together with this feature pyramid network that is useful really for working not only with the objects that are in foreground, but also with the objects that are in background. And using this FPN, we can have similar information of the objective of the people, even if they are at this different distance. And then we integrate everything in a final Roy pooling in order to have this estimation of the Gaussian of the distance of each point. Actually, is working well, really well, according to the comparison with other motion. But now, recently, we try to do something better. And so what we are trying to do is using this for the tracking, but the idea is that this is not for a single tracking, but using this 3D distance is able to improve every tracking actually we have. This is some numbers that have been used in ModScene, dividing easy, moderate, and hard scene, but also using in real data, and in general, we have an improvement. What we did recently, very recently indeed, is to try to have a more generalized distance evaluation, and not only for people, but also for vehicle and for other things. And the basic idea I can show you with just only one image is to include the upper part is exactly the same that I showed before, even the schema has different color. But what we added actually is a mask autoencoder that you see here. And mainly the mask difference is that instead of evaluating the distance of each object one after the other, we try to evaluate the distance of all of them together. And this is very important because people that are closer, probably they share the same distance. So we trained first this local encoder and decoder with the mask autoencoder in order to regenerate a shape like this one that you see. It's not for re-identification or for, filling, but just only to have this information also for the part of occlusion. And then we use this the local encoder, the first part of we train it, then for a global encoder to create the distance of each possible object. Actually, results are good, and the results are good also for cars in order to see the distance of that. Just to give you a qualitative example, look for this there. So we are able to estimate the distance of this object, this vehicle, also at 100 meters of distance or more. And we do the same also for humans or for people that have been detected in order to detect their distance. This is quite useful for for tracking and for understanding the scene and for many other things. So if I have other few minutes, instead I would like to go to another direction. So whenever I can detect object or I can detect the scene, I really would like to reason and planning to move robots in the scene. Unfortunately, in this case, we cannot use the data set that we have or jackpot data set, because in this case, we needed to simulate the environment and to reuse the environment of that. So I really would like that your data set could be used also in this, if you can reconstruct all the 3D scenes, yes, probably could be used for simulation, the motion of the subject. So we did a lot of work of that. It's just only, I say, an overview of what we are doing. Because, for instance, one of the example of the final goal is, okay, robot, go there, take my bag, not the other bag. Look, but be careful not to touch my shoes. So you can understand that the robot has a lot of things to understand and to do. But in this case, it's easier to do because there are many space simulators that can be. In particular, we use Habitat, but not only Habitat, because with Matterport also we reconstructed some area and some scene. This is, for instance, are some gallery estensive that we have in Modena. So many things. So first is classical, now is classical, but was actually new in 2018. That is the problem of visual language navigation. That means I give you a command and you have to move the robot until reach the result. In the standard visual language navigation protocol, the motion of the robot has been designed by a graph, and the motion is general. Instead, we change that in order to make the real, and so we ask the robot to have just only small step up on the left, on the right, on the down. We created actually a single transformer, a single end-to-end architecture that can be used for image encoding, instruction encoding, and moving the robot that has been presented in simulated pattern, but also in real data. In order to do that, we need a lot of data. Some of them are coming from Habitat. Some of them instead are recreated. This, for instance, is a work that Lorenzo Baraldi is presenting now in another workshop. So that is about creating the instruction, new instruction in order to have a larger data set to have this kind of things. Very, very quickly, other things that we are doing. This is a work that we presented 2 years ago in ICRA. That is about understanding the world that is around and asking the robot to go around just only with this measure of impact. So go around and do something and choose choose which is the best area that you didn't didn't acquire before, in order to have, I say, a search by curiosity. Then adding another part, we would like that the robot can explain what is looking for. And in this case, we added the speaker policy. They say we can decide when the robot has to speak or not. I give you an example of what we are doing here. So I don't know if it's working. I think, yes, it's working. Look, this robot. So this, we asked the robot to go around and to search for something in a room, but he has no information about 3D and no information about the road. But whenever he's going around and find something that is different, explain it by word. For instance, yeah, this is a bathroom, and so in this case you can add the information of the command, the vision, the navigation of the robot, and also the final explanation of that. Actually, this is something that we presented last year in ICRA. And this is the new one that we presented a few weeks ago in Japan, also in ICRA, together with Marco Pavone and other people of Stanford. That the idea is, since we have to go around, we have to recognize the region of that. In general, in the house now, there is not the cooking area and the dining area separated by a wall, but now are all together. And so what we are trying to do is to understand when a robot is in an area or another. In this case, we use also CLIP to have information. The architecture is a bit difficult to explain in 1 second, but again, in order to give you an example, now the robot is able to go around and to understand which is the area then is going. Finally, because, okay, the results are good. The last, but really last work is something we are doing now, is that not only to ask the robot to go around to understand where there is, but also to find an object in a very personalized item, so that I don't want the bag, but I want my bag. So the idea is to learn what we are doing, and for instance, and for this reason, we improved the habitat data set, including some objects. So we created the 3D object in habitat. This is something that we sent to NeurIPS now, and is that the idea is to put some object around and ask to the robot to find them specifically. So we use this number of objects that have been with several instances added to the data set. So, and they have been added manually in some place where is obvious to have this kind of object. So like, for instance, I say on the table and so on. And then, of course, we also now create a navigation agent that is able to go around to find the object and try to do that. This is working, but in order to work well, needs also the segmentation of that. And just to find to finish my presentation is a publicity of what you can see tomorrow. That is something about segmentation on the wild of the object that is useful for this kind of embodied vision that you can find that. Okay, I'm concluding my talk because so now we can leave the room for the other one, that say that now moving object like your robot or our robot or many other that are allowed to collect data as you did, but also to go to explore the scene with or without a goal, to understanding the scene, to detect and track people in 3D space, to explain what the robot is doing. And finally, I hope that after a lot of years, we can start to work in a real environment like this one that I discovered that has been presented in Seattle in 1962. Nobody of us was there at that time. And when this Hanna-Barbera movie cartoon we done, the author said, okay, we will have this kind of things in 2062. I hope that we will have before. Okay, thanks.
Thank you.
Due to the time constraint, I think we can accommodate like one question for Professor Gutierrez.
I have a question.
Okay.
Thanks, very interesting talk. First, last work you just said, the very last work, I think is the very match this workshop. I wish I could get more of this because you are trying to do open world panoptic tracking, and that's but specifically talking about moving toward like now reasoning and the language base. And one of the problems generally we have with the robotic is either we need to go to the simulation with less dynamic or no dynamic object, or real data we can do that, we can reproduce it in the robotics. Means my question is what's your suggestion about like, okay, those habitat, those things allow us to do robotic, but we cannot place a human. It means there is no dynamics there.
In fact, this is really a problem. For this reason, I divided the two. When we started with habitat, our idea was also to put moving
Human.
people around. Yeah, because this is the final topic. We tested the robot in a museum or around, but if you have people, you have to deal with them, not
Yes.
only because there is an occupancy of the space. But it was really difficult. I spent 1 year with one student to try to put in habitat a moving person, but was too complex.
And that would be limited to the most case dynamic of that. Not really we are able to do more complex detailed interaction, right?
Yeah, I think that we have to think to something newer. So for instance, reconstruct 3D motion from video as the one you collected or similar.
That's true. But the time happens one time. That's the main problem with robotic. Means we cannot really re-simulate the human. If the base case, you can just build the environment empty from human, or you have the human in the same time, same view, nothing more, right?
Exactly. Now is something that we cannot do. So we divided the problem. We detected the human in one static or in video, and we do the other one.
Is there any suggestion what we do best for that? Means look like this is a kind of a stock, right? Means no simulation.
No, either to work in a virtual environment, completely virtual environment where everything can be reconstruction. Either try to do this without the reproducibility that we are used to have here in CVPR.
Sure.
Okay.
Thank you.
You're welcome.
So the next speaker is going to be Dr. Bole Yo. They left after the span. This for the recording. So I'm excited to introduce Dr. Bole Zhou, and he's an assistant professor at UCLA. So Professor Zhou focuses on creating interpretable and generalizable embodied AI that aligns with human intentions, exploring properties such as explainability, interpretability, steerability, generalizations, and safety. So his notable contributions include the development of class activation mapping, the places in ADE 20K dataset. And recently his work has extended to the project like meta drivers and a driving simulator for autonomous research and GenForce, which he presented yesterday at another workshop. I was there. So please join me to welcome Professor Bole Zhou.
Okay, yeah, so very happy to be here because we have a small group. So feel free to ask me any questions during the talk. Right. So today, I would like to share with you some of our efforts to build some simulator to support this kind of a human simulation as well as a urban environment simulation. So nowadays we have many existing work that try to pioneering the mobility on the roads, right? A lot of autonomous driving companies out there. So they are building these vehicles to support this mobility on the roads. But I will see the future will be the mobility anywhere. So here I'm showing you a video in West LA. So it's a robot from the Coco Robotics. So it's a startup in LA. So the co-founder actually graduated from UCLA. So they are doing this kind of food delivery bots. Basically, they already have more than 100 such bots deliver the food orders across the city. Right. So they are running this kind of robots on the sidewalk. So compared to this mobility on the road, then you can see there's a sidewalk navigation. It's much more challenging, right? So you have a lot of pedestrians there and a lot of this obstacles like potted plants and the tree roots. So right now their operations is just the teleoperation, which means there is some human sit behind the cameras and the remote control this small size vehicles. Right, so you can imagine we can include some autonomy, then we can have this kind of human AI share control, so that can greatly improve the operation cost of this business. Then from this example, we have a delivery bot on the sidewalk. So not only we have this delivery bot, we have many other mobile machines gradually emerging in the sidewalk and the urban space, cohabiting with humans, such as we also have this power wheelchair, right? So human will just disable, and the elder people will use a joystick to control this electric wheelchairs. Also, nowadays we have a lot of this legged robots, such as robot dog and the humanoid robots, like from different companies. So those legged robots will also operating on the sidewalk. But operating on the sidewalk is very challenging, right? So we have this mobile machines that are trying to operating on the sidewalk, but the sidewalk situation I would say is much worse on the road, right? So first of all, we have people, right? We have the crowds. So the robots have to interact with this crowd behaviors. Also for the infrastructure, right? So we have this rigid terrains and also this broken curbs. So it's very challenging for those mobile robots to navigate. Also on sidewalk, we have a lot of crazy behaviors, like those homeless people also put tents on the sidewalk. So in the case, in order to have this mobile machine operating on the sidewalk, we have to ensure the safety and the generalizability of these machines. So it's very challenging to do so, right? So one possible solution is maybe we can annotating more images, right? So I guess that's the effort of the Jackrabbit robots try to annotate more data, then we can segment and understand the visual things more, such that we can make a better decisions. So keep annotating more images could be one solution. Another solution could be how can we build a simulation, right? So then we can train and evaluate those robots in the environment before the real world deployment. So the simulators become more and more important in this embodied AI and the robotics research, right? So here I show you some of the existing simulations built by the community to support this embodied AI research. So we have this like Gibson environment. Also for the driving environment, we have MetaDrive as well as this color environment. But there are multiple issues out there. First, there is no simulator, at least the popular simulator for public urban space simulation. Also, many of the existing environments don't have human inside. So they are more like a ghost town or ghost house, right? No human inside. So in order to tackle this issue, so along with my student and the postdoc, so we are trying to build a new urban environment simulator. here is a demo video showing you our initial results, right? So we can simulate different sidewalk environments that we can place the 3D asset on the roads. And we also have a lot of mobile agent, like pedestrians and many other like scooters and this power wheelchairs. Then we can use this algorithm to help us randomize those assays and generate a lot of environments. So this environment is actually built on top of MetaDrive. So for those of you who don't know what is MetaDrive, so here is a quick overview on the MetaDrive. So we start developing this MetaDrive simulators like 3 years ago. So it's an open source driving simulator. You know, compared to the existing ones such as Kala, we want to follow a data-driven simulation, which means we allow user to generate new environments by sampling from the predefined traffic blocks, such as this intersection, roundabout. Then we can turn this generated scenario into this interactive environment. Then we can put agent inside for training and evaluation. So the MetaDrive is very efficient. So on a standard PC, it can run more than 500 FPS. We also open source at this link. So far it has been downloaded more than 40,000 times, have hundreds of stars at the GitHub. Another key properties of the MetaDrive is that we also build the dataset behind. So we build the dataset layer, allow user to input the real world data in the simulation, right? Basically, we want to implement this real to scene concept to bring real world data into the simulation. So we have the ScenarioNet project published at the NeurIPS last year that allow us to load a lot of real world traffic scenarios into the simulator. So this demo video showing you this traffic scenarios loaded from the Waymo new plan, and also we have the procedure generated scenarios. So we have more than 500,000 traffic scenarios, so which is much larger than the existing manually decide like town environment in Kala. So based on the MetaDrive, so we are developing this meta urban. Basically, we want to shifting towards this sidewalk simulation, because I would say the sidewalk simulation is much more interesting because we have different human behaviors. Also, we have a lot of mobile machines that can operate on the sidewalk. Right? It's also related to this urban planning, meaning this city poverty research. So now, in order to create this diverse environments, so we follow this hierarchical procedure generation of the environment. Basically, we can use some configure file to define how many blocks we want, what the structure we want. Then we can generate a roadmap, right? So after we have the roadmap, then we follow some urban planning booklet. Then we can divide those road into different functional zones, like those zones that we can place static objects, then which zones are for the pedestrian walking, right? And also place this lamp and the trees inside. After we have this functional zones, then we will retrieve the asset from the objectives. It's actually a little bit similar to what prior speaker Rita did, right? Bring some new asset from this objectives, which is a very large scale 3D repositories. Then we can place those assets in our created environments. We also can randomize those assets. Then we can create different simulated environments. So the images on the right showing you the same layout of objects. Then we can have a different asset, so we can create different visual appearance. So in a case, we can basically have an infinite number of environments. Then we can use them for training and evaluation. Not only we have this static object, we also want to populate this simulated environment with dynamic agents. So on the left, I show you a full spectrum of a mobile agents. So not only we have different pedestrians, we also have a different mobile machines. So on the right, I'm showing you a parade of this mobile machine, right? So we have not only pedestrian and also this food delivery bots and many other lector robots. So after we have the static environment as well as a mobile agent, then we can use this environment for some interactive training. So this is a table showing you some benchmarks we built on top of the meta urban. So the first task, we have tried this social navigation. So basically for this environment, we place some static object and also some traffic mobile agents. Then we want to train this ego like food delivery bot to do this destination reach task. So here the table showing you the different algorithm like reinforcement learning algorithm, offline IO, and the imitation learning. So that is a very challenging task. Compare so far for the static environment like point navigation. So we only have like 60% accuracy. For the social navigation, which have a mobile agent inside, the performance even lower. Which means then there are a lot of space for this research opportunity. Like how can we develop better navigation agent to understand this dynamic environment? So this demo video showing you reinforcement agent we trained in testing time. So it's just a Coco robot, the delivery bot, try to navigate inside the environment, try to avoid those dynamic agents and reach the destination. And then you can imagine after we have this environment, we can design some other tasks such as language guided navigation or mounted this environment generation with some large language model. Then we can generate more diverse behaviors and define more interesting tasks. It also can support many machine autonomy research. So we also build this human interface. Basically, we have human subject that can it's more like play a video game, like do this demonstration, and we can collect the human demonstrations. One existing issue is that you may notice this pedestrian, their behavior is more like walking like a zombie, right? So it's we just have this rule-based animation for those pedestrians. So that is fine for this navigation task, but for many other tasks, then we want to have a more diverse pedestrian behaviors. Then the challenge is how can we improve the realism of pedestrian behaviors? So then what we are looking into is those YouTube videos. So if you search the YouTube videos, you will get a lot of this on the left side, city walking videos. Basically, there are YouTubers, they will mount some GoPro camera on their heads and walking in different cities. So they will record those videos. Then we can apply this 4D human estimation measure to extract this 4D human pose from those data. Then we can train some motion synthesis network on top of the extracted data. Then we can simulate these different diverse pedestrian behaviors. So then you can see here on the right, showing you some of the knowledge model. We sample from them, then they can generate very diverse pedestrian behaviors. Right. So that can help us address this existing issues for motion synthesis. This the current most popular data set for motion synthesis is AMS, and this is also MotionX data set. But the issue is that they don't have this diverse annotation for the scene context. They have a lot of human activities, but they don't have this naturalistic human pedestrian behaviors, also how human behave in the scene context. So in the case, we are collecting a large scale human motion data set in the wild. So it's called a city walker data set. So far we have 34,000 subjects from 11,000 scenes from this 30 hours of YouTube videos. So this demo video showing you the different YouTube video we have, and this 40 human estimators we extract, right? So we can have then you can see there is a lot of diversity out there, right? So different cities, different visual appearance, and the different pedestrian behaviors. Right, so here are some this diverse pedestrian behaviors we have, like leaning on a stroller and turning, and also taking out phones and take a picture, and poking into a wall, right? So moving items. So a lot of diverse behaviors that happen on the sidewalk. So those data can help us better simulate this diverse behaviors that may happen on the sidewalks. So after we have the data, then we want to then develop some generative model. So here is a context-aware generative model we developed for this pedestrian movement generation. Because we noticed that for the pedestrian behavior, it's very important to model the context factors. So there are multiple context factors we should take into consideration. The first is surrounding environment, right? So that like traffic size will largely affect how pedestrians move in this scene on the street, right? And also this pedestrian behavior also related to this individual like a features, right? There's age, weight, gender, right? So they have a different behaviors depending on this individual people. Also, the goal is also important, right? So because most of the case, the pedestrians have a very clear goal to reach, right? They are not randomly moving on the street. So in the case, we built some transformer-based model that try to incorporate this different scene context inside, try to model the geometry of the scenes, body shape, and the goal of the person. Then this transformer then can help us decode this trajectories. So here are some of the generation results. One thing I should emphasize that this model can actually work with this 2D image directly. So the input right now is just this 2D image, the same from the YouTube video, right? So we don't have this 3D annotation for the scene, just 2D image. We just apply some pseudo label predictor that can give us a pseudo depth, then use that as the input. Then we can generate this context-aware motion, human motions. So here showing you the generation in the real images. So so right now it's just the first frame of the real scene. Then we estimate the pseudo depth labels. Then use this as the input to the model. Then it can give us this pedestrian behaviors. So here's another one, right? So given their initial pose, then we can continue generating those behaviors. So right now we don't take into consideration of the social factor. That is our next step. Like right now, this people just individually generated. So I think it should be flexible to introduce this social factor, like generate 2 or 3 a group of people at the same time. Also, we can use this training model to feed into the simulators. So here is a scene image from the color simulator, right? Then we can generate this diverse pedestrians moving around inside this environment. Here another one, right? So try to walking inside the scenes. Also, the people become larger and larger, which means this model really learns this geometry of the scenes, right? It can so we did some quantitative evaluation to verify how important different context factor is. Right, so here is a ablation study. Like after we include this scene context and the goal and the humans, we can have the best performance after we take all the factor into consideration. We also compare with the method that without this context modeling, right? So then you can see without context modeling, then the generated motions cannot be sensitive to the motion. Okay, so guess I can skip this part. So quickly go through this part is we want to further improve the visual appearance of the simulators, right? So then we have another recent work that called the SingGen that can help us leverage the text to image model to convert this simulated environment into the realistic scenes, right? So in the case, we also try to mix the data from both the simulator and the YouTube video, right? And then we develop some simulator conditioned driving scene models that can help us generate the realistic scenes. Here are some of the results, like giving this simulated environment frames. Then this model can re-render this image into more realistic images, condition on the text prompt given by the users. The different frames and different synthesized results. Skip this part. So finally, here are some other CVPR papers we will present in the next few days. Like here is a free control measure, which is also tried to help us re-render this simulated environment into realistic image. So basically, this is more like a training-free control net. Right, so control nets, you need to pair wise annotations, but for this free control, you don't need to train anything. So we just use this image to manipulate the cross attention layer. Then we can generate different appearance condition on the user text prompt. You have another one like this 3D mesh. Then we can re-render this into different image. Also, we can mount this work with this like text to image model to help us do this text guided 3D generation. So here another work will be presented at CVPR that we allow user to write different texts as input. Then it can help us generate this 3D environments. So here is a bedroom with large windows, like with mountain, snow mountain range views, and also here a bedroom with aerial view of skyscrapers outside. In Mongol style, also here is we can type this bedroom on fire, right? So can give us this realistic 3D scenes. So potentially we can further input this generated scenes in our simulator and run this like social navigation or this whole robot to improve their generalizability in new environments. Okay, so then I will just stop here. So for the Meta Urban, so we will release this Meta Urban environment in August. So right now we try to clean up the code. Yeah, so happy to answer any questions you have. Thank you. Yeah.
I'm curious, is the simulator learning anything with the interaction between the human agents and the world itself?
Yeah, so for the motion synthesizer work, so we put this surrounding into the model, right? So when we try to train the model to synthesize the motion, so we will have the local scene context as input. Basically, it's a depth pseudo depth map.
So like because the sliding, like the humans are walking, even if they don't actually walk like a certain gait, they keep moving in the environment. Like
I see.
So I guess.
Yeah, so in a case, if you want to have a better, more realistic ones, then there should be some physics. Then you have to incorporate some physics engine here to create some gravity. So that can give you more realistic result. So right now we don't have.
The simulator learns the contacts between the legs and walking itself. I guess you could probably fix it.
Yeah, I think that's you want to fix that, you have to incorporate some physical engines. Some basically have some physics, like have some gravity there.
Yeah.
So right now this one is more like in the space, no gravity. Then it's hard for the physical model to learn this real world physics.
So it's learning human motion, but.
Yeah.
how exactly?
Without knowing the gravity.
Yeah.
Mhm.
My question is about the, when you generate realistic scenes from, you give the model the generated image and generate images of streets and Tokyo and is it deterministic in a way you can generate the same street the day, night, summer, winter?
I think here is we utilize the stable diffusion model, right? So stable diffusion model will have some stochasticity insight. So if you just resample that, like if you like the same thing you want to generate nighttime, then probably they cannot ensure the consistency. Yeah.
I have one question if you don't mind. About City Walker data set.
Okay.
Is it the one you show? It's the only videos, or the data? Is it along with the 3D, and is it annotation, or is it just algorithm generated? Okay.
Yeah. To help us clean up a little bit, but right now we don't have a human annotation.
I see.
Yeah.
I see.
So I think it would be great if we can have some human annotation to correct some labels. And also we notice a lot of missing detection result, even some occlusion because the street is quite busy, right? So the 4D human estimator actually doesn't work so well. So we just filter out those data with the data. Yeah, thank you.
Thank you.
Yeah.
Yep. Thank you, Professor Joe. So our next speakers. Professor Milford is he's a professor at Queensland University of Technology, the director of QUT Robotics Center, and a Microsoft Research Faculty Fellow. His interdisciplinary research emulates neuromechanisms in the brain to develop cutting-edge technologies for autonomous vehicles and other challenging applications. He's also a passionate educator and advocate for the societal impacts of emerging technologies. So please join me in welcoming Professor Michael Milford.
Hi, can you hear me okay? Can you hear me okay and see my screen? Whoop.
Let me check if you can.
I think people online can hear, but we
can hear.
can't hear.
Hello, can you hear me?
Can you use your laptop?
Yeah.
Can you see my screen or hear me?
Michael, if you hear us, just wait a minute. I think we have the audio coming from.
Yeah, the audio is bad.
Okay.
Can hear.
Yep. Let's try
Test,
again.
testing. Can you hear me?
Yeah, we can hear you. Yeah.
Okay, awesome. Are you okay for me to get started?
Yes, you can.
Okay.
Okay.
Yeah, that's good.
Okay, awesome. Fantastic. Look, thanks so much for inviting me to present, and apologies I couldn't be there in person. I have a hard deadline for another talk at 5:15 p.m. Local Seattle time, so I may skip a few slides just to make sure we stay on time. Thanks to the organizers, and I'll get into it. So the two topics within the workshop scope that I'll be talking to are particularly the, I guess, the segmentation aspect of things, scene understanding aspect of things, and also some comments about metrics and performance measures for perception problems relating to autonomous robots and vehicles. I'll talk about two areas of research: contextual hazard detection and improving segmentation using place priors, and then talk a little bit about a need for better metrics, especially for environments which have people in them and are safety and operationally critical. And then talk about I think, an under-investigated area, which is introspection, and talk about why I think that is important as well. So just briefly, I come from the QT Centre for Robotics. We're a large research centre in Brisbane, Australia. We do robots in just about every environment on Earth, in the sea, underneath the sea, in the skies, in medical theatres, on land and deep underground as well. And so we learn a lot about developing robot systems. And many of these do have to work in collaborative or interactive environments with people around. My particular research group has done a lot of work in positioning for autonomy. So this is autonomous
I think you are on mute.
Sorry, can you hear me again?
Yeah, it's good now. Yeah.
Yeah, the Zoom call has dropped out a couple of times, and I'm pretty sure it's not on my end, so I don't know. Can you see my screen still?
Yes, we do.
Okay, fantastic. Let me just skip forward to, I guess, the first piece of research I want to talk about. So this is contextual hazard detection. And so I guess one of the things we learned early on in our journey in working in areas like mining and trying to work in areas like construction is that you can't just run straight object pipelines. If you're worried about things like trip hazards, which are obviously a concern in environments populated by both people and environments, the context in which the object you find is important. And so a great example of this is a ladder. So a ladder leaning up against a wall on a construction site is not really a major trip hazard for most people, but a ladder when it's lying down on the ground is a significant trip hazard because you won't necessarily see it as easily. And so this is work led by a PhD student at the time, Sean McMahon, looking at how we can automatically detect the context in which objects like trip hazards appear and assess their level of danger to people working in the environment. So I won't go into much detail about this, but we looked at a number of hazards that are relevant to both people and autonomous vehicles and robots. So water, snow, rubble, and drop-offs. Drop-offs are a particularly interesting thing. How can you detect a drop-off like a cliff when you can't necessarily directly observe the cliff? And so we have a number of results in that paper. I won't go into too much detail, but I guess the key result from this work was that you can't just run straight object detection pipelines when you're worried about hazards or understanding scenes. You need to understand the context in which those objects appear in order to really assess their danger to people and robots operating in that environment. The second piece of work I want to talk about, which is more recent, was our work in trying to improve semantic segmentation in very challenging conditions. So the field of semantic segmentation has made substantial strides in recent years, but it's still very hard to semantically segment scenes under very challenging visual conditions. So imagine in a snowstorm or in heavy rain in the middle of the night. So there's been progress made, but to do this at a level with vision only that's satisfactory for safety critical operations like autonomous vehicles is quite challenging. And so one of our researchers, Connor Malone, has led a lot of work in this area. And you can see a bunch of publications at the bottom if you want more details. So the idea we had here was related to our work in localization and visual place recognition areas. And it was based on the observation that a lot of places in the world are semantically similar, especially in domains like road-based domains. And in some respects, making a visual place recognition algorithm or a visual localization algorithm high performing in these challenging conditions is easier than making a semantic segmentation pipeline work to the same level of performance. And we also looked at some of the weaknesses of visual place recognition algorithms, or what is normally considered as a weakness, which is their viewpoint dependence, which means that if you change the perspective with which you view a scene, your visual place recognition system may stop working, and considered this a strength for the approach that I'm just about to present. So the idea here was to use similar place priors. So as one of your last speakers pointed out, there is a lot of data available on the internet and more widely. And so what we did here was we developed a pipeline where, to do semantic segmentation, we'd take the input image, the query image, we would compare it using a visual place recognition pipeline to thousands or millions of images in a database. We'd find semantically similar places from around the world, and we would perform segmentation on those places under ideal visual conditions, and segmentation tends to work better. And then we would use the segmentations from those similar places that aren't from the same geographical location to bias the segmentation on the actual image we were interested in the first place in segmenting. And so we did this for the road class, which is obviously a big class of interest for autonomous driving. This is the basic pipeline. So you can see that we're segmenting the image of interest directly, but we're also segmenting the images of places that have been found around the world that look similar, especially under better conditions. There are some other aspects to this, like averaging the top K similar places to smooth out the volatility, but this is the basic idea. And in a nutshell, it works reasonably well. So you can improve the performance of any baseline semantic segmentation pipeline by looking up similar places in good conditions, performing semantic segmentation on those similar places, and then biasing the segmentation of the query image that you're currently segmenting. We extended this work in some more recent research to all semantic classes. Essentially, what we found was that this approach of finding similar places tended to work best on semantic classes that have large regions, so road, vegetation, not so much things like poles or things that are very small objects in the field of view. All right, so that's I guess, just a couple of areas where we're trying to improve the understanding of robots and autonomous vehicles with respect to the scene that they move through and their understanding of what the different parts of that scene mean in terms of moving through safely through that environment. The second thing I want to talk about is some observations we've had from a range of projects over the years that I think are interesting in terms of metrics and how we conduct research in the area. I'm not going to talk about all of these. I'm going to talk about metrics that we use to assess performance and whether they're fit for purpose, and the value of introspective capability. So all of these insights have been, I guess, spurred by working in a range of industry and applied projects. We're not sort of abstractly thinking about this. These insights have come up in the process of working on projects with industry partners. So the first one, in the localization field, a typical localization paper, this is from our CVPR 2021 paper, will have a table like this with your bold numbers for your method, which works better than hopefully the state-of-the-art methods at the time. And in localization, the typical measures used are recall at 1, recall at 5, recall at 10, and recall under various location and angular tolerances. Recall at 1 just means of the best ranked match returned from your system, is it in the correct place, and so on. Now, one of the things we found, which was really confusing at the time, was we were working on creating better localization systems for autonomous vehicles. And this is a graph of performance. So a high bar is better performance, split up into roughly, I think, 1 kilometer segments of road for one of the, I think this is the Ford autonomous vehicle data set. So the blue bars are where the system's performing relatively well at a tolerance of 0.25 meters. And the red bars are where the system is not performing very well. So we made a bunch of architectural and system changes to our system to improve the worst case performance. So basically to stretch those red bars further in the vertical so that the worst case performance in those challenging 1 kilometer sections of road was substantially improved. And sometimes that came at the slight cost of some of the performance in the other areas. And what we found, which was really interesting, is this wasn't making any difference to the metrics that we would report in a CVPR or a robotics ICRA paper. So basically, we were making changes that made a huge difference to worst case performance of the vehicle, but they were invisible in terms of the conventional metrics that we all report in our papers. And this is a good example of that in practice. And again, this is an environment where you would expect lots of people around and where I think we need to think about the metrics that we use. So here are two different localization scenarios, 1 and 2. They both have the same overall localization performance. So blue means the car knows where it is, and red means the car doesn't know where it is. So this is scenario 1. You can have a look at it. And this is scenario 2. So these have the same recall at 1 performance. So they'd look invisible, they'd look identical from the terms of those metrics. But this second scenario, we would argue, is much more desirable for multiple reasons. One is that the points in the environment where it is failing to localize, the red dashed lines, are points that are not near areas of the environment that are particularly likely to have pedestrians and vulnerable road users near them. The second reason is the periods of time when the vehicle is not well localized are much shorter. And so you have more ability to compensate for those shorter periods of being lost, which is, I guess, fundamental to a lot of SLAM approaches as well. And so we would argue that there's a need for much better performance metrics, especially in operationally critical environments where people are involved. The second one I want to talk about is the power of introspection. Again, this relates to robots that are operating around people or interacting with people or have to be very critically safe in order to not hurt people. So again, we're going to start with two scenarios. And this is really about knowing when you don't know. And this could be for a localization system. It could be for a pedestrian recognition system. It could be for any aspect of robotic system performance in a crowded environment occupied by people. So this is localization system 1. It works 99.9% of the time, but it lacks self-diagnosis capability. So when it's not working, it doesn't know it's not working. It can't report on it. System 2 only works 99% of the time, but of that remaining 1% of the time when it's not working well, it's able to self-diagnose that it's not working 99% of that remaining time. Now, if you're in a safety critical environment, which I would argue is anyone where there are robots around people, system 2 is vastly superior because you'll only unknowingly act on incorrect positional information 0.01% of the time. And so it's an order of magnitude better in that respect than system 1, even though system 1 is what would look better perhaps in a conventional research paper. So this relates to a number of areas. So this is Helen Carson, who's just finishing her PhD in our lab. These are not all the same concepts, but they all have some relationship to each other. So the provability, the auditability, the trust you would place in these autonomous systems and so forth. And so Helen's been doing a lot of work, as well as some other researchers in the lab, on adding integrity and introspection capabilities to existing localization pipelines. So the basic idea is you add these integrity measures or assessment monitors over the top of the system, and you're able to check whether the output is likely to be correct or whether you should discard it. In this case, it's discarding the output. Why is this important? Well, I'd argue it's probably one of the most important things and probably one of the least investigated areas in computer vision, robotics, and autonomous systems. So you can stop if you know when you don't know. You can hand off collaboration to people in the context of robots interacting with people. The robot can signal that it's in trouble to the pedestrians or people working around the robot so they know how to treat it. If terms of what the robot or autonomous system is doing, you can learn new representations if you're triggered by your system knowing that it's not performing very well. You could even trigger a complete relearning cycle if your system knows and self-reports that it's completely failing. So you have a lot of options, but the system has to know that it's not working well. This is another project led by PhD student Morgan Windsor in the surgical robotics domain. And again, there's paper references, including from this year at the bottom. In all domains, it's important to know when you don't know, but in particular, in a collaborative surgical robotics domain, it's important. You have a robot operating side by side with a surgeon. The surgeon is not always able to look at what the robot is doing and tell visually whether the robot's performing well or not. And so if the robot can self-report on its confidence in what it's doing, the surgeon knows when and if to take over, which is a critical part of collaborative automation. So that was, I guess, a relatively quick taster. I realize it was a little rushed, but hopefully I got across some of the key points. We have a bunch of further resources online. As I said, all the paper references were at the bottom of a number of those slides, and I'll share the slides with the workshop organizers. We're always interested in collaborating. So you saw what we did at the beginning of our slide, beginning of the presentation. So please reach out if you want to chat about work in any of these domains. We thank all of our funding agencies and collaborators, obviously our team and the QT Center for Robotics. And again, thank you to the organizers. This is the wrong slide for the end slide, but thank you to the organizers for organizing the workshop. It's a lot of work, and I hope your CVPR conference is going well for everyone. Thank you.
Okay, Michael, can you hear us?
Yes, I can.
Okay, good. Let me ask if anyone has a question. I have a couple of questions. Let me see if audiences have a question. I can pass the microphone. Can you?
Hello, Professor. I have a quick question on the security aspect of things, right? Safety critical systems, and I saw the work with the autonomous driving where you have to like make checks and keep moving. What's the future of this field? Like, how do you see like with autonomous driving becoming more of a bigger deal now, and you know, with more like autonomous systems being put into real world with humans especially, how do you see this field evolving with safety robotics?
I was at ICRA, the main robotics conference earlier this year, and it was refreshing to not be constantly talking about autonomous vehicles. Instead, we were mostly talking about large language models. So I guess the key themes change. Look, there's a lot of people at CVPR who are much more invested and know a lot more about autonomous vehicles than I do. I guess the main things I'd say in response to your question are, one, we're not solving all of these problems from scratch. So an autonomous vehicle is not a smartphone, and it's not a drone, and it's not an airplane. But there are significant aspects of best practice that have been proven over many years that we are adapting to the field of autonomous vehicles. But then, of course, there has to be some extra considerations for autonomous vehicles specifically. Good. I can see some of the people in the audience. Beyond that, in terms of security, it's a significant concern. Obviously, the weaponization of autonomous vehicles, or even more innocuous things like people being locked out of being able to use an autonomous vehicle is a concern. On the news, topically, I just saw that Wabi, the autonomous trucking company, just announced the $200 million Series A or B, I think. And so autonomous driving is still in the news, it seems.
Is there any other question? Michael, I have the. Can you hear me again? I'm just.
Yes, I can. I can hear you. Yep.
About the one you said, the report robot can report its confidence. How do you do that? Means how do you measure the knowledge of the of the robot and then try to report that confidence?
Oh, so look, that's a great question, and I'll answer quickly, but I'll just note that Helen is actually on the Zoom and can probably talk about this more offline. But basically, there's levels of sophistication. So the initial work that we did was relatively simple, but it really worked. So basically, training a binary classifier based on labeled data to assess whether the system is performing well or not performing well. Obviously, and this comes up often in discussion time, the next step up is to consider uncertainty and have a more sort of rigorous approach to that. But we were already able to achieve significant gains in performance just from a simple classification approach. And so there's a lot of room for potential future work in this area. And we and a number of others are definitely following up on this. There's a paper in CVPR from a group on this as well.
Do you have any other question? One more question. If the images you said about segmentation, difficult condition, how the annotation of that is provided? If we can, is it human annotated? Means for evaluation purpose, I mean.
Oh, yeah. So for the evaluation, just for assessing performance, we're using mostly existing ground truth provided with the data sets. In terms of the similar place prior segmentation, one of the beauties of that is we don't need the ground truth for that. We just perform a semantic segmentation on the image obtained from another similar place under ideal conditions, and it works pretty well. I think we did evaluate using actual ground truth for that, but I don't know whether it made much of a difference.
I'm curious to know how the ground truth is annotated. I mean, if at night is the like a human also cannot really distinguish some of those. I just want to curious to know how they, I don't know, is a public data set which try to create segmentation for them.
Yeah, I think I can talk to Connor, but I think we used relatively common segmentation data sets. I can check with him whether he had to do any manual laborious labeling of those more challenging conditions, because you're right, doing it automatically would not be trivial, given that's the problem we're trying to solve. All right, I have to run to another presentation. Sorry, thank you so much for the invite to present.
Thanks, Michael, for it's our pleasure to have you here. Thank you.
All right, I think that's the end of our workshop today. Thank you so much for joining. So a few last question, if you have any feedback on the JRDB dataset, or if you have any like usability, or what metric, what like challenge do you want the JRDB dataset to improve on, and please feel free to give us feedback.
All right.
Otherwise, yeah, all good. Hope you guys enjoy the next few days of the conference. Thank you. See ya.